The end meets the beginning. Everything comes full circle. In the dark vastness of space, we've always thought the universe stretches outward forever. But what if we're wrong? What if, like a snake eating its own tail, the universe curves back and connects to itself in ways we're just starting to understand? This idea of a looped universe isn't just a wild thought, it's a real possibility in modern physics. Einstein's theories allow for a universe that might be finite but without boundaries. If you traveled far enough in one direction, you could eventually return to where you started, similar to how we can circle our round Earth. Scientists have found intriguing hints in the cosmic microwave background, the oldest light in our universe. Some researchers believe there are matching patterns on opposite sides of the sky, possibly showing the same regions seen from different angles, like seeing your reflection in parallel mirrors. If the universe truly is a loop, it would change everything we understand about reality. Time and causality would work differently. Events in the distant future might somehow affect the past. The concepts of before and after would become circular rather than linear. A looped universe refers to a fascinating cosmological concept where space and time curve back on themselves, creating a closed, finite, yet unbounded structure. In this model, if you were to travel in one direction for an incredibly long time, you would eventually return to your starting point, much like circumnavigating the Earth. This idea challenges our intuitive understanding of the cosmos. Instead of an infinitely expanding universe with a clear beginning and potential end, a looped universe suggests a cyclical nature to existence. It proposes that what we perceive as the Big Bang might be just one phase in an endless cycle of expansion and contraction. The looped universe concept also has implications for our understanding of cosmic history and the future. In such a universe, the distinction between past and future could become blurred, as events might repeat in a grand cosmic cycle. This model raises intriguing questions about causality and the nature of time itself. While the looped universe remains a theoretical concept, it continues to captivate cosmologists and physicists. It offers an alternative perspective on the shape and destiny of our universe, prompting us to reconsider our place in the grand cosmic tapestry. The concept of a looped universe presents a fascinating challenge to our conventional understanding of cosmology. This idea suggests that our universe might be curved in such a way that it connects back on itself, much like the surface of a sphere. In this scenario, if you were to travel in one direction for an incredibly long time, you would eventually return to your starting point. This notion contradicts the prevailing view of a flat, infinite universe that extends endlessly in all directions. It forces us to reconsider fundamental aspects of our cosmic model, including the nature of space and time themselves. If the universe is indeed looped, it would have profound implications for our understanding of the Big Bang and the ultimate fate of the cosmos. One of the most intriguing consequences of a looped universe is its impact on our concept of infinity. In a closed, finite universe, there would be a limit to how far we could see or travel, even if that limit is unimaginably vast. This challenges our notions of the observable universe and raises questions about what might lie beyond our cosmic horizon. Furthermore, a looped universe could potentially explain some cosmological mysteries, such as the uniformity of the cosmic microwave background radiation. It might provide a mechanism for different regions of space to have been in causal contact early in the universe history, resolving the horizon problem without the need for cosmic inflation. However, current observations have not found evidence supporting a closed universe, leaving this intriguing possibility as a speculative but thought-provoking concept in modern cosmology. Throughout history, various cultures and philosophical traditions have proposed cyclical models of the universe. Ancient Indian cosmology, particularly in Hindu and Buddhist thought, conceived of the universe as undergoing endless cycles of creation, destruction, and rebirth. This concept, known as the Wheel of Time or Kalachakra, suggests that the cosmos experiences periodic dissolutions and re-emergences. In ancient Greek philosophy, the idea of eternal recurrence emerged. Philosophers like Heraclitus and later the Stoics proposed that the universe repeats itself infinitely, with all events and circumstances occurring again and again in a never-ending loop. This concept influenced Friedrich Nietzsche centuries later, who incorporated it into his philosophical works. Mayan civilization also held a cyclical view of time and the cosmos, with their complex calendar systems reflecting the belief in recurring world ages. Each age was thought to end in catastrophe before beginning anew. Similarly, ancient Egyptian mythology included the concept of cycles. With the daily journey of the sun, god Ra symbolizing the continuous renewal of the world. In modern times, some cosmological models have explored the possibility of a cyclic universe. The ekpyrotic scenario, proposed by Paul Steinhardt and Neil Turok, suggests that the universe undergoes endless cycles of expansion and contraction, with each cycle beginning with a Big Bang-like event. While these contemporary theories differ from ancient beliefs, they reflect an enduring human fascination with the idea of cosmic cycles and the potential for universal renewal. The concept of a looped universe and the idea of a multiverse are two distinct theories in cosmology, each offering a unique perspective on the nature of our reality. A looped universe suggests that our cosmos is finite but has no boundaries, much like the surface of a sphere. In this model, if you were to travel in one direction for an incredibly long time, you would eventually return to your starting point. This idea challenges our intuitive understanding of space and proposes that the universe curves back on itself in higher dimensions. On the other hand, the multiverse theory posits the existence of multiple universes beyond our own. These universes might have different physical laws, constants, or initial conditions. The multiverse concept encompasses various models, including the many worlds interpretation of quantum mechanics and the idea of bubble universes arising from eternal inflation. While a looped universe deals with the geometry and topology of our single universe, the multiverse theory expands the scope to include numerous separate universes. The looped universe model attempts to explain the large-scale structure of our cosmos, whereas the multiverse theory addresses questions about the apparent fine-tuning of our universe and the nature of quantum reality. Both concepts challenge our understanding of the cosmos and push the boundaries of theoretical physics. However, they differ fundamentally in their approach to explaining the nature of existence, with one focusing on the shape of our universe and the other proposing a vast landscape of different universes. A looped universe is a fascinating concept in cosmology that challenges our traditional understanding of space and time. The key characteristic of such a universe is its closed topology, where space essentially folds back on itself. In this scenario, if you were to travel in one direction for a long enough time, you would eventually return to your starting point. This looped structure implies that the universe has no boundaries or edges. Instead of extending infinitely in all directions, it curves around to connect with itself. This curvature might not be detectable on small scales, much like how the Earth appears flat from our perspective on its surface, despite being a sphere. Another defining feature of a looped universe is the potential for repeating patterns or structures. If light from distant objects has had time to circle the universe multiple times, we might see repeated images of the same galaxies or cosmic structures in different directions in the sky. This phenomenon could create a cosmic hall of mirrors effect, where the observable universe appears much larger than its actual size. The concept of a looped universe also has implications for the nature of time. In some theoretical models, time itself might loop, leading to a cyclical universe that repeats its entire history. This idea challenges our linear perception of time and raises profound questions about the beginning and end of the universe. The concept of a looped universe challenges our understanding of fundamental physics in profound ways. If our cosmos were indeed a closed loop, several key principles would require significant re-evaluation. Firstly, the law of causality would face serious scrutiny. In a looped universe, events could potentially influence their own causes, creating paradoxes that defy our current understanding of cause and effect. This would force us to reconsider the very nature of time and its unidirectional flow. The principle of conservation of energy might also need revision. In a closed-loop system, energy could theoretically be recycled indefinitely, challenging our notions of entropy and the arrow of time. This could have far-reaching implications for thermodynamics and our understanding of the universe's ultimate fate. Furthermore, our concepts of infinity and boundlessness would require re-examination. A looped universe implies a finite yet unbounded space, much like the surface of a sphere. This would necessitate a fundamental shift in our approach to cosmology and the nature of space itself, potentially altering our interpretation of general relativity and quantum mechanics. Entropy and the concept of a looped universe are intricately connected, presenting a fascinating interplay between thermodynamics and cosmology. Entropy, often described as a measure of disorder in a system, tends to increase over time according to the second law of thermodynamics. In the context of the universe, this suggests a gradual progression towards a state of maximum disorder and uniformity, often referred to as heat death. The idea of a looped universe, however, proposes that the cosmos might undergo cycles of expansion and contraction, potentially resetting the entropy clock with each new cycle. This cyclical model challenges the linear view of entropy's inexorable increase. In a looped universe scenario, the end of one cosmic cycle could theoretically lead to conditions similar to the beginning of the next, creating a sort of reset button for entropy. However, this concept faces significant challenges. Critics argue that entropy would still accumulate across cycles, leading to larger and longer expansions in each subsequent iteration. This accumulation could eventually break the cycle, resulting in a universe that expands indefinitely or collapses into a final singularity. The relationship between entropy and a looped universe highlights the tension between our understanding of thermodynamics and the desire for a cyclical cosmic model. It underscores the complexity of reconciling fundamental physical laws with grand cosmological theories, pushing scientists to explore new ideas and potentially revise our understanding of the universe's long-term fate. General relativity forms the cornerstone of our understanding of a potentially looped universe. This groundbreaking theory, developed by Albert Einstein, describes how space and time are interwoven into a four-dimensional fabric called spacetime. It explains that massive objects warp this fabric, creating what we perceive as gravity. In the context of a looped universe, general relativity provides the mathematical framework to explore how space-time might curve on a cosmic scale. It allows scientists to model scenarios where the universe could connect back to itself, forming a closed loop in higher dimensions. This concept challenges our intuitive understanding of a flat, infinite cosmos. General relativity also predicts the existence of exotic space-time geometries that could support a looped structure. These include wormholes and closed time-like curves, which theoretically allow paths through space and time to loop back on themselves. While highly speculative, these ideas stem directly from the equations of general relativity. Furthermore, the theory helps us understand how light and matter would behave in a looped universe. It predicts how cosmic structures would form and evolve, and how we might detect signs of a closed topology through observations of the cosmic microwave background radiation. General relativity thus serves as the lens through which we can explore and potentially verify the mind-bending concept of a universe that loops back on itself. Quantum mechanics offers intriguing insights that both support and challenge the concept of a looped universe. At the quantum level, particles can exist in superposition, occupying multiple states simultaneously until observed. This phenomenon suggests that reality might be more fluid and interconnected than classical physics indicates, potentially allowing for complex universal structures like loops. The idea of quantum entanglement, where particles remain connected regardless of distance, hints at a deeper underlying fabric of space-time. This interconnectedness could theoretically support the notion of a universe that loops back on itself, with distant regions maintaining intrinsic connections. However, quantum mechanics also presents challenges to the looped universe concept. The uncertainty principle, a cornerstone of quantum theory, implies fundamental limits to our ability to measure certain pairs of physical properties precisely. This inherent uncertainty might make it difficult to definitively prove or disprove a looped universal structure. Furthermore, quantum decoherence, the process by which quantum systems interact with their environment and lose their quantum properties, could potentially disrupt the delicate balance required for a stable looped universe. As we scale up from quantum to cosmic levels, maintaining quantum effects becomes increasingly challenging, potentially undermining the quantum support for a looped universal structure. The concept of a looped universe, also known as a closed universe, has intrigued cosmologists for decades. While direct observational evidence remains elusive, several phenomena hint at this fascinating possibility. One key piece of evidence comes from studies of cosmic microwave background radiation, the afterglow of the Big Bang. Some researchers have identified unusual patterns in this radiation that could potentially indicate a universe that wraps around on itself, creating a vast cosmic loop. Another intriguing observation involves the distribution of galaxies and galaxy clusters across the observable universe. Some studies have suggested that there might be repetitive patterns in this distribution which could be consistent with a universe that loops back on itself. However, these findings remain highly debated within the scientific community. Gravitational lensing, the bending of light by massive objects in space, has also provided tantalizing clues. In a looped universe, we might expect to see multiple images of the same distant objects appearing in different parts of the sky. While some candidates for such multiple images have been identified, conclusive proof remains elusive. It is important to note that while these observations are intriguing, they do not provide definitive proof of a looped universe. Many alternative explanations exist, and the vast scales involved make it challenging to gather conclusive evidence. As our observational techniques and technologies continue to advance, astronomers and cosmologists eagerly await new data that might shed more light on the true shape and nature of our universe. The Big Bounce theory presents an alternative to the widely accepted Big Bang model of the universe's origin. It suggests that our universe undergoes cycles of expansion and contraction rather than having a single starting point. According to this concept, the universe expands until it reaches a maximum size, then begins to contract due to gravity, eventually collapsing in on itself. This collapse, however, does not mark the end. Instead, the immense energy and density at the point of collapse trigger another expansion, creating a new cycle. This theory relates closely to the idea of a looped universe, where time and space form a closed loop rather than a linear progression. In a looped universe model, the end of one cycle seamlessly transitions into the beginning of the next, creating a perpetual cosmic dance of expansion and contraction. The Big Bounce provides a mechanism for this loop, explaining how the universe might transition from one cycle to the next. Proponents of the Big Bounce theory argue that it solves some puzzling aspects of the Big Bang model, such as the singularity problem. In the Big Bang theory, the universe begins from an infinitely dense point, which is difficult to reconcile with our current understanding of physics. The Big Bounce avoids this issue by proposing a universe that never actually reaches that problematic infinite density. While the Big Bounce theory remains speculative and faces its own challenges, it offers an intriguing perspective on the nature of our universe. It invites us to consider the possibility that our cosmos might be part of a grand, cyclical process, eternally renewing itself through successive expansions and contractions. Cosmic inflation and the concept of a looped universe present intriguing possibilities for the structure and history of our cosmos. Inflation theory suggests that in the earliest moments after the Big Bang, the universe underwent a period of exponential expansion, growing faster than the speed of light. This rapid growth smoothed out irregularities and set the stage for the universe we observe today. The idea of a looped universe, on the other hand, proposes that the universe might be finite but have no boundaries, much like the surface of a sphere. In this model, if you travel far enough in one direction, you would eventually return to your starting point. While this might seem at odds with the concept of a rapidly expanding universe, some theories attempt to reconcile these ideas. One possibility is that cosmic inflation could have occurred within a pre-existing looped universe, causing a small region to expand dramatically and become our observable universe. In this scenario, our visible cosmos would be just a small part of a larger, looped structure. Alternatively, inflation might have created multiple universe bubbles, some of which could have looped geometries. These concepts challenge our understanding of the universe and highlight the complex interplay between different cosmological theories. As scientists continue to explore these ideas, new observations and mathematical models may help us better understand how inflation and a potentially looped universe structure could coexist. The cyclic model, proposed by cosmologists Paul Steinhardt and Neil Turok, offers an alternative explanation for the origin and evolution of the universe. This theory suggests that our universe undergoes endless cycles of expansion and contraction rather than having a single beginning point like the Big Bang theory proposes. In this model, our three-dimensional universe is conceived as existing on a membrane, or brane, within a higher dimensional space. This brane periodically collides with another parallel brane, and each collision initiates a new cycle of expansion for our universe. The energy released during these collisions is believed to be responsible for the creation of matter and the subsequent expansion we observe. The cyclic model attempts to address some of the challenges faced by the standard Big Bang theory, such as the horizon problem and the flatness problem, without relying on the concept of cosmic inflation. It suggests that the apparent uniformity and flatness of our universe result from the cumulative effects of numerous cycles, rather than from a brief period of exponential expansion in the early universe. While the cyclic model presents an intriguing alternative to the Big Bang theory, it remains a subject of debate within the scientific community. Researchers continue to explore its implications and seek observational evidence that could support or refute this fascinating concept of a cyclical universe. Roger Penrose's conformal cyclic cosmology presents a fascinating alternative to the conventional view of the universe's fate. This theory suggests that our universe is just one in an endless series of universes, each beginning with a Big Bang and ending in a state of extreme expansion. According to Penrose, as our universe continues to expand and cool over incredibly vast timescales, all matter will eventually decay into radiation. At this point, the universe becomes essentially scaleless, as all particles have been reduced to massless photons. This state, Penrose argues, is mathematically identical to the conditions of the Big Bang that started our universe. The key to this cyclical model lies in the concept of conformal geometry, which focuses on the angles between objects rather than their size or distance. Penrose proposes that when the universe reaches this maximally expanded state, it becomes indistinguishable from a highly compressed state, setting the stage for a new Big Bang. This theory effectively stitches the end of one universe to the beginning of the next, creating a continuous cycle of universes. Each cycle, or aeon as Penrose calls it, would have its own laws of physics and potentially different fundamental constants, making it distinct from the universes before and after it. The ekpyrotic universe theory offers an alternative explanation for the origin and evolution of our cosmos. It suggests that our universe began not with a sudden explosion, but with a slow, drawn-out collision between two vast, sheet-like structures called branes. These branes exist in a higher dimensional space and periodically collide, sparking the creation of new universes. In this model, the universe goes through cycles of expansion and contraction. Each cycle begins with the collision of branes, which releases enormous energy and creates the conditions for a new universe to form. As this universe expands and cools, it eventually reaches a point where it begins to contract again, leading to another brane collision and the birth of yet another universe. This cyclical process challenges the idea of a singular beginning to time and space. Instead, it proposes an eternal series of universes, each born from the remnants of its predecessor. The ekpyrotic theory attempts to solve some of the puzzles left unanswered by the Big Bang model, such as the flatness and horizon problems, without relying on the concept of cosmic inflation. While the ekpyrotic universe theory remains controversial and lacks definitive observational evidence, it continues to intrigue cosmologists as a potential alternative to the standard Big Bang model. It represents one of several attempts to understand the deepest mysteries of our cosmos and the nature of its origins. In a looped universe, the geometry of spacetime would take on fascinating and counterintuitive properties. Unlike our familiar concept of space extending infinitely in all directions, a looped universe would curve back on itself, creating a closed yet boundless structure. This unique geometry would have profound implications for how we understand distance and direction. An object or light beam traveling in what seems to be a straight line would eventually return to its starting point, having traversed the entire universe. This looping effect would occur in all three spatial dimensions, creating a complex, multidimensional torus-like structure. The curvature of spacetime in a looped universe would be positive, similar to the surface of a sphere, but extended to higher dimensions. This would result in some intriguing phenomena. For instance, an observer might see multiple images of the same distant galaxy in different directions, as light from that galaxy reaches Earth by traveling around the universe in various paths. Time, too, would be affected by this looped geometry. While the exact nature of temporal loops in such a universe is speculative, it is possible that time itself might exhibit cyclic properties, potentially leading to scenarios where the past, present, and future interconnect in ways that challenge our linear perception of time. A closed universe is a model of the cosmos where space curves back on itself, much like the surface of a sphere. In this scenario, the universe has a finite volume but no boundaries. If you were to travel in a straight line for long enough, you would eventually return to your starting point, similar to circumnavigating the Earth. This concept relates to the loop idea in cosmology, which suggests that the universe might have a cyclical nature. In a closed universe, the total mass and energy are sufficient to eventually halt the expansion caused by the Big Bang. Gravity would then cause the universe to contract, potentially leading to what some scientists call a big crunch. The loop concept proposes that this big crunch could be followed by another Big Bang, creating a new cycle of expansion and contraction. This idea of a repeating cosmic cycle aligns with the closed universe model, as both involve a finite yet unbounded space. However, current observations suggest that our universe is actually expanding at an accelerating rate, which challenges the closed universe model. Nevertheless, the concepts of a closed universe and cosmic loops continue to intrigue scientists and inspire further research into the nature and fate of our cosmos. In a looped universe, the curvature of space would vary significantly across different regions, creating a fascinating tapestry of cosmic geometry. Near massive objects like galaxies and black holes, space would curve more sharply, bending light and altering the paths of nearby celestial bodies. These areas of intense curvature would form pockets of highly warped spacetime, potentially creating gravitational lenses that distort our view of distant objects. As we move away from these dense regions, the curvature would gradually flatten out, becoming less pronounced in the vast expanses between galaxies. In these cosmic voids, space might appear nearly flat, with only subtle variations in curvature detectable through precise measurements. However, on the largest scales, the overall curvature of the universe would loop back on itself, connecting distant regions in ways that might seem counterintuitive to our everyday experience. The boundaries of this looped universe would present particularly intriguing curvature properties. As we approach these edges, space might begin to curve more dramatically, eventually wrapping around to connect with the opposite side of the universe. This could result in unusual visual phenomena, where we might theoretically see multiple images of the same galaxy as light travels along different paths around the loop. Understanding these variations in spatial curvature is crucial for cosmologists studying the large-scale structure of the universe. By mapping out these changes, scientists can gain insights into the distribution of matter and energy throughout the cosmos, as well as the fundamental nature of space and time themselves. A toroidal universe structure would fundamentally change our understanding of cosmic geometry and the nature of space itself. In this scenario, our universe would be shaped like a giant donut, with unique properties that differ significantly from our current model of a flat or spherical cosmos. One of the most intriguing implications would be the possibility of seeing multiple versions of the same objects in different directions. As light travels around the donut shape, it could potentially circle back to its starting point, creating the illusion of repeating patterns in the night sky. Astronomers might observe galaxies or other celestial bodies appearing to exist in multiple locations simultaneously. This toroidal structure would also impact our concepts of infinity and boundlessness. While the universe would be finite in volume, it would have no edges or boundaries. An observer could theoretically travel indefinitely in any direction, eventually returning to their starting point, much like circumnavigating the Earth. The curvature of space in a toroidal universe would affect gravitational forces and the movement of light in ways that could challenge our current understanding of physics. It might require revisions to theories of cosmic inflation, the distribution of matter, and the nature of dark energy. Such a universe structure would provide a fascinating new framework for cosmologists to explore and potentially explain some of the mysteries that currently puzzle scientists in our quest to understand the cosmos. Detecting the curvature of a looped universe presents a fascinating challenge for cosmologists. One potential method involves studying the cosmic microwave background radiation, the afterglow of the Big Bang that permeates the entire universe. Scientists analyze the patterns in this radiation, looking for repeating structures or unusual alignments that might indicate a curved, finite universe. Another approach focuses on observing distant galaxies and quasars. In a looped universe, we might see multiple images of the same cosmic objects appearing in different directions or at different distances. This phenomenon, known as topological lensing, could provide evidence of a universe that curves back on itself. Advanced gravitational wave detectors might also play a role in this cosmic quest. These instruments could potentially pick up echoes or repetitions in gravitational wave signals, suggesting that the waves have traveled multiple times around a looped universe. Researchers are also developing mathematical models and computer simulations to predict what other observable effects a curved, finite universe might have on the distribution of matter and energy across cosmic scales. As our observational technologies and theoretical understanding improve, we may uncover more subtle signs that could reveal the true shape of our cosmic home. In a looped universe, our understanding of time would be fundamentally altered. Instead of a linear progression from past to present to future, time would curve back on itself, creating a closed time-like curve. This means that events in the universe would repeat in a cyclical manner, with the end of one cycle seamlessly flowing into the beginning of the next. The concept of cause and effect would become more complex in such a universe. An event in the future could potentially influence the past, creating what physicists call a causal loop. This challenges our conventional notions of causality and raises intriguing questions about free will and determinism. From the perspective of an observer within this looped universe, time might appear to flow normally. However, if one could somehow step outside the loop and view the universe as a whole, they would see that all moments exist simultaneously, much like points on a circle. This perspective aligns with the block universe theory, which posits that past, present, and future all exist at once. The implications of a looped universe for entropy and the arrow of time are profound. In our current understanding, the universe tends towards increasing entropy or disorder over time. However, in a looped universe, this progression would need to reset at some point, raising questions about how the laws of thermodynamics would function in such a system. The concept of time in a looped universe presents fascinating possibilities. In our current understanding of the universe, time appears to flow in one direction, from past to future. This is known as the arrow of time, closely tied to the second law of thermodynamics and the increase of entropy. However, in a looped universe, the nature of time could be fundamentally different. Such a universe would essentially wrap around on itself, potentially allowing for a cyclical rather than linear progression of events. This could theoretically create situations where the end of time connects back to its beginning, forming a closed time-like curve. In this scenario, time might not strictly flow in one direction as we perceive it. Instead, it could exhibit bidirectional properties, where past, present, and future exist simultaneously in a loop. This could lead to paradoxical situations, such as events influencing their own causes or information traveling backwards in time. Yet, even in a looped universe, the subjective experience of time for observers might still appear unidirectional due to the thermodynamic arrow of time. The increase in entropy could create a perceived flow of time in one direction, even if the underlying structure of the universe allows for bidirectional movement. This interplay between cosmic structure and our perception of time continues to challenge our understanding of the universe and remains an active area of theoretical research. The concept of a looped universe presents intriguing challenges to our understanding of the arrow of time. In our current model, time flows in one direction, from past to future, guided by the increase of entropy as described by the second law of thermodynamics. However, if the universe were a loop, this linear progression would be fundamentally altered. In a looped universe, the end would connect back to the beginning, creating a cyclical structure of spacetime. This arrangement could potentially result in a repeating cycle of events where the arrow of time might appear to reverse or lose its clear directionality. The distinction between past and future could become blurred, as events that we consider to be in the distant past might also be in the far future. This cyclic nature could have profound implications for causality and the accumulation of entropy. In a traditional linear universe, entropy increases over time, leading to the eventual heat death of the universe. But in a looped universe, this progression might be reset or redistributed at the point where the loop closes, potentially allowing for a perpetual cycle of cosmic evolution and devolution. The idea of a looped universe challenges our fundamental notions of time and raises questions about the nature of memory, free will, and the very fabric of reality. It forces us to reconsider whether time is truly a one-way street or if it might be more akin to a circular path, forever returning to its starting point while simultaneously moving forward. The concept of multiple timelines in a looped universe is a fascinating idea that pushes the boundaries of our understanding of space and time. In theoretical physics, some models propose the existence of parallel universes or multiple timelines, each representing different possibilities or outcomes. When we combine this with the notion of a looped universe where time might cycle back on itself, we enter a realm of mind-bending possibilities. In such a scenario, we could imagine different timelines coexisting like threads in a complex tapestry, each following its own path, but potentially intersecting or influencing others. These timelines might represent alternate versions of events, diverging at critical moments and creating distinct realities. In a looped universe, these timelines could theoretically repeat endlessly, creating a cosmic dance of infinite possibilities. However, it is crucial to note that while these ideas are intriguing, they remain firmly in the realm of theoretical physics. Current observational evidence does not support the existence of multiple timelines or a looped universe. Scientists continue to explore these concepts through mathematical models and thought experiments, pushing the boundaries of our understanding of the cosmos. The implications of such a universe would be profound, challenging our notions of cause and effect, free will, and the nature of reality itself. It raises questions about whether events in one timeline could influence another, or if we could ever be aware of these alternate realities. As we continue to unravel the mysteries of the universe, these thought-provoking ideas inspire us to look beyond our current understanding and imagine the extraordinary possibilities that might exist in the vast expanse of space and time. In a looped cosmos, our understanding of past and future would be fundamentally altered. This fascinating concept challenges our linear perception of time, blurring the boundaries between what has been and what will be. Imagine time as a circular path rather than a straight line. In this scenario, events we consider the distant past could also be seen as the far future. The end of the universe might seamlessly connect to its beginning, creating a continuous cycle of existence. This loop structure would mean that cause and effect become intertwined, with future events potentially influencing past occurrences. Such a cosmic loop would have profound implications for the arrow of time. The second law of thermodynamics, which states that entropy always increases, might need to be re-evaluated. In a closed loop, the total entropy of the universe could remain constant, challenging our understanding of cosmic evolution and the heat death of the universe. Moreover, the concept of a looped cosmos raises intriguing questions about free will and determinism. If events repeat infinitely, one might argue that all actions and decisions are predestined. However, the complexity of such a vast cosmic cycle could still allow for variations and unpredictability within each loop, preserving the essence of choice and possibility. In a looped universe, the concepts of a beginning or end point become fundamentally different from our usual understanding. This cosmological model suggests that the universe curves back on itself, creating a closed loop in both space and time. As a result, the traditional notions of a starting point or final destination lose their conventional meaning. Imagine traveling in one direction through this looped universe. You would eventually return to your starting point, not because you reached an end and turned back, but because the very fabric of space-time brought you full circle. This concept challenges our intuitive understanding of linear time and finite space. In such a universe, every point could be considered both a beginning and an end, depending on your perspective. The distinction between past and future becomes blurred, as events could potentially influence themselves in a causality loop. This mind-bending idea suggests that the universe might be self-contained and self-perpetuating, without the need for an external cause or a defined endpoint. However, it is important to note that while the looped universe model is an intriguing theoretical concept, it remains speculative. Current observational evidence does not conclusively support or refute this idea, leaving cosmologists to continue exploring various models of the universe's structure and evolution. The concept of a looped universe presents a fascinating alternative to the traditional Big Bang theory. In this model, our universe undergoes an endless cycle of expansion and contraction rather than having a definitive beginning. This cyclical nature challenges the idea that the universe started from a single point of infinite density and temperature. In a looped universe scenario, what we perceive as the Big Bang might actually be a transition point from a previous cycle of contraction to a new phase of expansion. This suggests that our universe could be much older than current estimates, potentially even infinitely old. The looped model proposes that the universe expands, reaches a maximum size, then begins to contract under its own gravity, eventually collapsing back to a highly compressed state before bouncing back into expansion. This cyclic view of the cosmos raises intriguing questions about the nature of time and causality. If the universe has no true beginning, it challenges our understanding of how the fundamental laws of physics came to be and why the universe exists in its current form. It also addresses the question of what came before the Big Bang, suggesting that there was always a universe in some form. However, the looped universe concept faces its own challenges. It must explain how the universe overcomes entropy and maintains its ability to expand and contract indefinitely. Scientists are still debating whether such a model can be reconciled with our current observations and understanding of cosmic evolution. Despite these hurdles, the idea continues to intrigue cosmologists as they seek to unravel the mysteries of our universe's origins and ultimate fate. In a universe that cycles through periods of expansion and contraction, the concept of heat death would be replaced by a more dynamic process of cosmic renewal. Instead of a final, unchanging state of maximum entropy, this looping universe would experience periods of rebirth and reorganization. As the universe contracts, gravitational forces would overcome the expansion, causing matter and energy to condense. This compression would lead to extreme temperatures and densities, potentially triggering a new Big Bang event. The intense conditions during this contraction phase would effectively reset the universe, redistributing energy and matter into a new, low-entropy state. This cyclic model suggests that our universe might be part of an endless series of expansions and contractions, each cycle lasting billions or trillions of years. The transition between cycles would serve as a cosmic reset button, erasing the effects of entropy accumulation and allowing for the formation of new structures and complexity in the subsequent expansion phase. However, it is important to note that while this cyclic model offers an alternative to heat death, it faces its own challenges and uncertainties. Scientists continue to debate whether such a model is compatible with our current understanding of physics and cosmology, and whether the universe could truly maintain this cycle indefinitely without some form of degradation or energy loss between iterations. The concept of multiple Big Bangs in a looped universe model is an intriguing possibility that challenges our understanding of cosmic origins. This idea suggests that our universe might undergo cycles of expansion and contraction, with each cycle beginning with its own Big Bang. In this scenario, the universe would expand from a singularity, much like in the standard Big Bang model. However, instead of expanding indefinitely, it would eventually slow down, stop, and then begin to contract under the force of gravity. This contraction would lead to what some scientists call a big crunch, where all matter and energy collapse back into a singularity. The key aspect of this model is what happens next. Proponents of the looped universe theory propose that this singularity could then spawn another Big Bang, initiating a new cycle of cosmic expansion. This process could potentially repeat indefinitely, creating a series of universes, each with its own Big Bang. While this concept is fascinating, it remains highly speculative. Current observations suggest our universe is expanding at an accelerating rate, which poses challenges for the looped universe model. However, scientists continue to explore various theories about the ultimate fate and potential cyclical nature of our cosmos, seeking to unravel the mysteries of our universal origins and destiny. In a looped universe, cosmic rebirth takes on a fascinating dimension. As the universe expands and eventually reaches its maximum size, it would then begin to contract. This contraction would lead to what cosmologists call the Big Crunch, where all matter and energy collapse back into an incredibly dense state. This process of expansion and contraction could potentially repeat indefinitely, creating a cycle of cosmic death and rebirth. Each new cycle would begin with its own Big Bang, expanding outward from the remnants of the previous universe. This perpetual loop would mean that our current universe might be just one iteration in an endless series of universes. The concept of cosmic rebirth in this model suggests that the fundamental laws of physics and the initial conditions of each new universe could be slightly different. This variation might lead to diverse universal properties and structures in each cycle. Some scientists speculate that information or certain characteristics from previous cycles might even be carried over into subsequent universes. However, it is important to note that while the idea of a looped universe is intriguing, current observational evidence points more towards an ever-expanding universe. The concept remains a topic of theoretical discussion and continues to inspire both scientific inquiry and philosophical contemplation about the nature of our cosmos and its potential cyclical existence. In a looped universe, matter would exhibit some intriguing behaviors that differ from our current understanding of the cosmos. One of the most striking differences would be the potential for objects to appear multiple times from different angles. Imagine looking through an incredibly powerful telescope and seeing the back of your own head, because light has traveled all the way around the universe. This looped structure would also affect the distribution of matter on the largest scales. Instead of the relatively uniform distribution we observe in our universe, a looped universe might show patterns or symmetries that repeat at regular intervals. These patterns could provide clues about the size and shape of the universal loop. Gravity would behave differently in a looped universe as well. Objects near one edge of the loop could be gravitationally influenced by matter on the opposite side, leading to unexpected movements and formations. This could result in unusual galaxy clusters or cosmic structures that defy our current models of galaxy formation and evolution. Furthermore, in a looped universe, the concept of cosmic expansion would need to be re-evaluated. The expansion we observe might be more complex, possibly involving the stretching of the loop itself rather than a uniform expansion in all directions. This could lead to unique challenges in understanding the long-term fate of such a universe and how matter within it would evolve over cosmic timescales. In a cyclical universe model, energy undergoes a fascinating journey of transformation and conservation. As the universe expands and contracts in each cycle, energy shifts between different forms but remains constant overall, adhering to the fundamental law of energy conservation. During the expansion phase, the universe cools and matter forms, with gravitational energy converting into other types such as kinetic and thermal energy. Stars and galaxies emerge, fusing lighter elements into heavier ones and releasing tremendous amounts of energy in the process. As the expansion slows and reverses, these structures begin to break down and energy becomes more concentrated. In the contraction phase, the universe heats up dramatically. Matter breaks down into its constituent particles, and eventually, all forms of energy merge into an incredibly dense, hot state, similar to the conditions just before the Big Bang. This process effectively resets the universe, preparing it for the next expansion cycle. Throughout these cycles, the total energy of the universe remains constant, but its distribution and form change dramatically. This perpetual transformation of energy from one state to another drives the cosmic dance of expansion and contraction, creating a universe that is ever-changing yet fundamentally conserved in its totality. In a looped universe scenario, dark matter and dark energy could indeed play distinct and fascinating roles. Dark matter, the invisible substance that interacts gravitationally with normal matter, might serve as the cosmic scaffolding that helps maintain the structure of the universe throughout its cycles. As the universe expands and contracts, dark matter could act as a stabilizing force, ensuring that galaxies and large-scale structures remain relatively consistent from one cycle to the next. Dark energy, on the other hand, could be the driving force behind the expansion phase of each cycle. Its repulsive nature might propel the universe outward until it reaches a critical point, after which the loop begins to contract. In this model, dark energy might not be constant, but could vary in strength or even change its properties throughout the cycle, potentially switching from a repulsive to an attractive force. The interplay between dark matter and dark energy in a looped universe could create a delicate balance, with dark matter providing the gravitational pull to initiate the contraction phase, while dark energy fuels the expansion. This dynamic relationship might be crucial in determining the duration and characteristics of each cosmic cycle. Furthermore, the behavior of dark matter and dark energy across multiple cycles could potentially leave subtle imprints on the cosmic microwave background or influence the distribution of galaxies, providing clues about previous iterations of the universe and shedding light on its cyclical nature. The conservation of energy principle, a fundamental law of physics, would play a crucial role in a looped cosmic system. In such a scenario, the total energy of the system would remain constant, even as it cycles through different forms and states. In a looped cosmic system, we might observe energy transformations on a grand scale. For instance, the gravitational potential energy of massive cosmic structures could convert into kinetic energy as they collapse, which in turn could generate intense heat and radiation. This energy might then disperse, eventually cooling and reforming into new structures, starting the cycle anew. The fascinating aspect of a looped cosmic system is that it would challenge our understanding of entropy and the arrow of time. While the second law of thermodynamics suggests that entropy always increases in a closed system, a truly cyclical universe would need a mechanism to reset or reverse this process. This could involve exotic physics or phenomena we have yet to discover or understand fully. Such a system would also have profound implications for the fate of the universe. Instead of the heat death or big freeze scenarios often discussed in cosmology, a looped system would suggest a universe that continually renews itself, potentially existing indefinitely. This concept pushes the boundaries of our current physical models and invites us to explore new realms of theoretical physics. As matter approaches the transition point of the cosmic loop, it would experience extreme and unprecedented physical conditions. The fundamental forces of nature would begin to behave in ways we can barely comprehend, with gravity becoming increasingly dominant. The intense gravitational effects would cause matter to stretch and compress, a phenomenon known as spaghettification. Time itself would start to warp and slow down from the perspective of an outside observer. From the viewpoint of the matter crossing the transition point, time might appear to speed up dramatically. The very fabric of space-time would become highly curved and distorted, potentially creating gravitational lensing effects that would bend light in strange and unpredictable ways. As matter crosses this cosmic threshold, it might undergo a phase transition, changing its fundamental properties. Atoms could be torn apart, with subatomic particles potentially transforming into forms of exotic matter we have yet to discover or fully understand. Some theories suggest that information about the matter's original state might be preserved on the surface of the transition point, similar to how information is thought to be stored on the event horizon of a black hole. The fate of matter beyond this cosmic boundary remains one of the greatest mysteries in modern physics. It could be recycled into a new universe, converted into pure energy, or experience something entirely beyond our current scientific understanding. This transition point represents the ultimate frontier of our knowledge about the universe and its underlying structure. The concept of a universe forming a loop is intriguing and relates to the shape and topology of the cosmos. To understand this, we need to consider spatial dimensions beyond our familiar three. In theory, a universe could form a loop with as few as one dimension, but this would be an extremely simplified model. In a more realistic scenario, scientists propose that our universe might form a loop in 4 spatial dimensions. This idea is part of the concept known as a closed universe or finite universe. In this model, if you were to travel in a straight line in any direction for an incredibly long time, you would eventually return to your starting point, much like circumnavigating the Earth. However, it's important to note that current observations suggest our universe is flat and possibly infinite, rather than curved and finite. The shape of the universe remains an open question in cosmology, and researchers continue to gather data and refine theories to better understand the true nature and geometry of our cosmic home. The possibility of higher dimensional loops in the fabric of spacetime is also explored in some advanced physics theories, such as string theory, which proposes additional compact dimensions beyond the four we experience. These extra dimensions could potentially form tiny loops, too small for us to detect directly, but with profound implications for the fundamental nature of reality. Cosmic topology explores the overall shape and structure of the universe, delving into its geometry and potential connections on the largest scales. This field of study examines whether space is finite or infinite, flat or curved, and if it possesses any unusual properties or configurations. One intriguing concept in cosmic topology is the idea of a looped universe. This notion suggests that the cosmos might be connected in ways that allow light and matter to traverse seemingly separate regions of space, creating a closed loop. Imagine traveling in one direction for an incredibly long time, only to find yourself back where you started, similar to circumnavigating the Earth. In a looped universe, space could be finite yet boundless. This means that while the universe has a limited volume, it has no edges or borders. Such a configuration might arise from the way space-time was shaped in the early moments of the Big Bang, resulting in a cosmic structure that folds back on itself. The concept of a looped universe challenges our intuitive understanding of space and raises fascinating questions about the nature of reality. If our universe were indeed looped, it could have profound implications for our observations of distant galaxies and the distribution of matter throughout the cosmos. However, current observations have not provided conclusive evidence for or against this intriguing possibility, leaving it an open question in the realm of cosmology. The concept of a looped universe extending into higher dimensions is a fascinating possibility that pushes the boundaries of our understanding of space and time. The concept of a looped universe challenges our intuitive understanding of space and raises fascinating questions about the nature of reality. If our universe were indeed looped, it could have profound implications for our observations of distant galaxies and the distribution of matter throughout the cosmos. However, current observations have not provided conclusive evidence for or against this intriguing possibility, leaving it an open question in the realm of cosmology. The concept of a looped universe extending into higher dimensions is a fascinating possibility that pushes the boundaries of our understanding of space and time. While we experience 4 dimensions in our everyday lives, 3 of space and 1 of time, theoretical physics suggests the potential for additional spatial dimensions beyond our perception. In a looped universe model involving higher dimensions, our observable universe might be just one part of a larger, multidimensional structure. These extra dimensions could be compact, curled up so tightly that they are undetectable at our scale, yet they could play a crucial role in the overall geometry and topology of the cosmos. The presence of higher dimensions in a looped universe could potentially explain some of the mysteries we observe in our 4-dimensional spacetime. For instance, they might account for the apparent weakness of gravity compared to other fundamental forces, or provide insights into the nature of dark matter and dark energy. Moreover, these additional dimensions could offer new pathways for the universe to connect with itself, creating complex topological structures that go beyond simple loops. However, it is important to note that while these ideas are mathematically consistent and intriguing, they remain highly speculative. Detecting or proving the existence of higher dimensions poses significant challenges, as our current technology and methods of observation are limited to the 4 dimensions we can directly experience. Nonetheless, the exploration of these concepts continues to drive theoretical physics forward, inspiring new ways to understand the fundamental nature of our universe. The shape of a looped universe in higher dimensional space is a fascinating concept that challenges our everyday understanding of geometry and space. In this scenario, our universe could take on a form known as a three-torus, often described as a donut-like shape, but existing in 4 spatial dimensions. Imagine our three-dimensional space curved and connected in all directions. As you travel in any straight line, you would eventually return to your starting point, much like how walking in a straight line on the surface of Earth brings you back to where you began. However, unlike Earth's surface, this looping occurs in all 3 dimensions simultaneously. This higher dimensional shape allows for some intriguing possibilities. In a three-torus universe, light from distant galaxies could reach us from multiple directions, potentially creating repeating patterns in the night sky. It might even be possible to see multiple versions of our own galaxy from different angles, if the universe is small enough relative to our observable portion. While the three-torus is one possible shape for a looped universe, other more complex topologies could also exist in higher dimensions. These might include various hypersurfaces or manifolds that are difficult to visualize but can be described mathematically. The true shape of our universe remains an open question in cosmology, with ongoing research and observations aimed at uncovering its underlying geometry and topology. String theory and its extension, M-theory, offer intriguing possibilities for understanding the concept of a looped universe. These theories propose that the fundamental components of our universe are not point-like particles, but tiny vibrating strings of energy. These strings exist in multiple dimensions beyond the 4 we can observe, potentially up to 11 dimensions in total. In the context of a looped universe, string theory suggests that the extra dimensions could be curled up or compactified in various ways. One possibility is that these extra dimensions form closed loops, much like a circle or a donut shape. This configuration could allow the entire universe to exist in a looped state where space and time curve back on themselves. M-theory takes this concept further by introducing the idea of branes, which are higher dimensional objects that can interact with each other. In this framework, our universe might be a 3-dimensional brane floating in a higher dimensional space. The looped nature of the universe could arise from the way these branes are configured or how they interact with each other in the higher dimensional space. These theories also open up the possibility of multiple universes or a multiverse, where our looped universe might be just one of many interconnected or parallel realities. While these ideas remain highly speculative and challenging to test experimentally, they provide a fascinating theoretical framework for exploring the nature of our universe and its potential cyclical or looped structure. Astronomers searching for evidence of a looped universe would focus on the cosmic microwave background radiation, the afterglow of the Big Bang that permeates the entire universe. They would look for specific patterns or anomalies in this radiation that could indicate the universe has wrapped around on itself. One key observation would be the detection of matching circles in the cosmic microwave background. If the universe were finite and looped, we might see the same pattern of temperature fluctuations repeated in different directions of the sky. These matching circles would suggest that light has traveled all the way around the universe. Another potential sign could be found in the large-scale structure of the universe. If space were truly looped, we might observe repeating patterns of galaxy clusters and superclusters at vast distances. This would require extremely precise measurements and observations spanning enormous cosmic scales. Gravitational waves could also provide clues. As these ripples in space-time travel through a looped universe, they might create distinctive interference patterns detectable by advanced gravitational wave observatories. Such patterns could reveal the shape and topology of cosmic space on the largest scales. If our universe were indeed looped or had a closed topology, detecting repetitions or echoes in the cosmic microwave background, radiation would be a crucial piece of evidence. Astronomers and cosmologists would look for patterns that repeat across vast distances in the sky, far beyond what we would expect in a flat or open universe. These repetitions would manifest as matching temperature fluctuations in the cosmic microwave background radiation. Scientists would use advanced statistical analysis and pattern recognition algorithms to search for these correlations. They would examine the radiation data collected by specialized telescopes and satellites, looking for areas of the sky that show nearly identical patterns of hot and cold spots. One challenge in this search is that any repetitions would likely be subtle and distorted by the vast distances involved. The radiation would have traveled for billions of years, potentially being affected by intervening matter and energy. Therefore, researchers would need to account for these distortions in their analysis. If such repetitions were found, it would suggest that light has had time to travel completely around the universe at least once since the cosmic microwave background was formed. This discovery would have profound implications for our understanding of the shape and size of the universe, potentially indicating that it is finite rather than infinite in extent. Gravitational waves, ripples in the fabric of space-time, could potentially serve as a powerful tool in uncovering the structure of our universe. If our universe has a looped or circular topology, these waves might provide crucial evidence. In a looped universe, gravitational waves could theoretically travel around the entire structure, eventually returning to their point of origin. This would create a distinctive pattern of echoes or repetitions in the gravitational wave signals we detect. Scientists could analyze these patterns to determine if they are consistent with a finite, closed universe. Moreover, gravitational waves from the early universe, particularly those generated during cosmic inflation, might carry imprints of the universe's overall shape and size. By studying these primordial waves, researchers could potentially identify signatures that indicate a looped structure. However, detecting such evidence presents significant challenges. The signals would likely be extremely faint, requiring highly sensitive instruments and sophisticated data analysis techniques. Despite these hurdles, as our gravitational wave detection capabilities advance, we may gain new insights into the fundamental nature and shape of our cosmos. Observing or measuring the connective point where the universe loops back on itself presents a significant challenge for cosmologists. This concept, often referred to as a closed universe model, suggests that space curves back on itself in higher dimensions, similar to how the surface of a sphere connects back to itself. To detect such a connective point, scientists would need to look for specific patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. If the universe were indeed closed and finite, we might observe repeating patterns or unusual correlations in this ancient light, as the radiation could have traveled multiple times around the universe. Another potential method involves studying the geometry of space on the largest scales. By precisely measuring the angles of enormous cosmic triangles formed by distant galaxies, researchers could potentially determine if space is flat, open, or closed. A closed universe would exhibit angles that add up to more than 180 degrees. However, current observations suggest that the universe is extraordinarily close to being flat, making the detection of any curvature or connective point extremely difficult with our present technology. Future advancements in space-based telescopes and gravitational wave detectors may provide the sensitivity needed to reveal such subtle cosmic structures, if they exist. Gathering empirical evidence for a looped universe presents significant challenges due to the vast scales involved and our limited observational capabilities. One major obstacle is the sheer size of the observable universe, which extends roughly 93 billion light-years in diameter. This immense distance makes it difficult to detect any potential repetitions or patterns that might indicate a looped structure. Another challenge lies in distinguishing between a truly looped universe and other cosmological phenomena that could produce similar observational effects. For instance, certain patterns in the cosmic microwave background radiation might suggest a looped structure, but they could also be explained by other factors, such as quantum fluctuations during the early universe or even observational artifacts. Time poses yet another hurdle. If the universe is indeed looped, the time required for light to travel around this loop might be far greater than the current age of the universe. This means that even if we are living in a looped universe, we might not be able to observe its effects within our cosmic horizon. Lastly, our current understanding of physics breaks down at extreme scales and energies, particularly when it comes to reconciling quantum mechanics with general relativity. This limitation in our theoretical framework makes it challenging to develop robust models and predictions for a looped universe that we can test through observations. In a looped universe, galaxy formation and distribution would exhibit fascinating and unique characteristics. Unlike our observable universe, where galaxies are spread out in a vast cosmic web, a looped universe would create a more interconnected and repetitive structure. Galaxies in a looped universe would form through similar processes of gravitational collapse and matter accumulation. However, their distribution would be significantly altered. As light and matter travel through the loop, they would eventually return to their starting point, creating a cosmic echo effect. This would result in multiple images of the same galaxies appearing at different points in the universe, potentially creating the illusion of a more densely packed cosmos. The large-scale structure of the universe would also be affected. Instead of expanding infinitely in all directions, cosmic filaments and voids would form repeating patterns as they loop back on themselves. This could lead to unusual galaxy cluster formations and potentially create cosmic hotspots where multiple loops intersect. Studying galaxy formation in a looped universe would present unique challenges for astronomers. Distinguishing between original and looped images of galaxies would require advanced techniques and could revolutionize our understanding of cosmic evolution and the nature of space-time itself. In a looped universe structure, cosmic voids and filaments might indeed form differently compared to our current understanding of the cosmos. This alternative topology could significantly impact the distribution of matter and the evolution of large-scale structures. Cosmic voids, the vast empty regions between galaxy clusters, and filaments, the thread-like structures connecting these clusters, are fundamental components of our universe's cosmic web. In a looped universe, these structures would be subject to unique gravitational influences and spatial constraints. The looped structure would create repetitive patterns of matter distribution, potentially leading to more uniform spacing of voids and filaments. This regularity could result in a more interconnected cosmic web, with filaments forming closed loops rather than extending indefinitely. Furthermore, the finite nature of a looped universe might affect the size and shape of cosmic voids. Instead of expanding indefinitely, voids could reach a maximum size determined by the universe's loop dimensions. This limitation could lead to a more densely packed cosmic structure, with smaller voids and more pronounced filaments than observed in our current model of the universe. The concept of a looped universe would dramatically alter our understanding of cosmic structure. In this scenario, instead of an ever-expanding cosmos, we would encounter a finite yet boundless space. Imagine traveling in one direction for an incredibly long time, only to find yourself back where you started. This looped structure would fundamentally change how matter is distributed on the largest scales. The cosmic web, composed of galaxy clusters, filaments, and voids, would take on new patterns and repetitions. We might observe the same structures recurring at regular intervals, creating a cosmic déjà vu effect for distant observers. Gravity would behave differently in a looped universe, affecting the formation and evolution of galaxies and clusters. The usual gravitational attraction between distant objects would be complemented by forces from their looped counterparts, potentially leading to more uniform matter distribution and altering the growth of cosmic structures. Light from distant galaxies would have multiple paths to reach us, potentially creating complex optical illusions and repeated images in the night sky. This could make cosmological observations and measurements incredibly challenging, forcing scientists to develop new methods to understand the true nature and history of our looped cosmos. In a looped universe, we would indeed expect to see repeating patterns in cosmic structure, but detecting them would be an immense challenge. This concept, often called a periodic or wraparound universe, suggests that if you travel far enough in one direction, you would eventually return to your starting point. Such a universe would likely exhibit large-scale structures that repeat at regular intervals. These could include galaxy clusters, cosmic voids, and filaments of dark matter that form the cosmic web. The repetition would occur at vast distances, potentially billions of light-years apart, making them extremely difficult to observe with our current technology. One intriguing possibility in a looped universe is that we might see multiple images of the same galaxies or cosmic structures, but at different stages of their evolution. This could provide a unique opportunity to study how these structures change over enormous timescales, offering insights into cosmic evolution that would be impossible in a non-looped universe. However, detecting these patterns poses significant observational challenges. The most distant objects we can see are already near the edge of the observable universe, and any repetitions would likely occur beyond this limit. Additionally, the expansion of the universe and the finite speed of light complicate our ability to detect such large-scale repetitions, even if they do exist. In a looped universe model, our understanding of cosmic horizons would undergo a significant transformation. The traditional concept of a cosmic horizon, which limits our view of the universe due to the finite speed of light and the expansion of space, would need to be re-evaluated. In this scenario, light from distant objects could potentially reach us from multiple directions, taking different paths through the looped structure of space. This would create a complex pattern of repeated images of the same celestial bodies, appearing at different distances and potentially at different points in their history. The observable universe in a looped model might extend beyond what we currently consider the particle horizon. Instead of a singular, spherical boundary of visibility, we could encounter multiple overlapping regions of observability. This could potentially allow us to see further into the universe's history than previously thought possible. Furthermore, the very nature of the cosmic microwave background radiation, which we currently interpret as the afterglow of the Big Bang, might need to be reconsidered. In a looped universe, this radiation could have traversed the entire loop multiple times, potentially carrying information from various epochs of cosmic history. In a looped universe, gravity would exhibit some intriguing and counterintuitive behaviors. This cosmic structure, also known as a closed universe, would fundamentally alter our understanding of gravitational interactions across vast distances. One of the most striking differences would be the potential for objects to exert gravitational influence on themselves. In a looped universe, light and gravitational effects could travel around the entire cosmos and return to their starting point. This means that a massive object, like a galaxy, might feel its own gravitational pull from multiple directions as its influence circles the universe. The concept of escape velocity would also change dramatically. In our observable universe, objects need to achieve a certain speed to break free from a gravitational field. However, in a looped universe, no matter how fast an object travels, it would eventually return to its starting point. This would create a cosmic version of a closed system where nothing can truly escape. Furthermore, gravitational lensing effects could become even more complex and pronounced. Light from distant objects might reach us multiple times, having traveled around the universe in different directions. This could create a hall of mirrors effect, with multiple images of the same cosmic structures appearing in different parts of the sky, challenging our ability to map and understand the true layout of such a universe. In a looped universe, the concept of varying fundamental forces across different regions presents a fascinating possibility. This idea challenges our understanding of physics and the nature of reality itself. The strength of fundamental forces like gravity, electromagnetism, and the strong and weak nuclear forces are typically considered constants throughout the observable universe. However, in a looped universe model, where space essentially wraps around on itself, we might encounter unique circumstances that could potentially affect these forces. One intriguing possibility is that as we traverse the loop, we might encounter regions where the fabric of space-time is distorted or stretched. This distortion could theoretically alter the local strength of fundamental forces. For instance, areas of highly curved space-time might experience stronger gravitational effects, while regions with less curvature might have weaker gravity. Furthermore, if the looped universe contains areas of varying energy density or exotic matter distributions, these could potentially influence the strength of fundamental forces in localized regions. This concept opens up a realm of possibilities for how the universe might behave on scales beyond our current observational limits, challenging our assumptions about the uniformity of physical laws across cosmic distances. The looped structure of the cosmos, a concept that suggests our universe might be connected back on itself in higher dimensions, could have profound implications for electromagnetism. This fundamental force, which governs the behavior of charged particles and light, might exhibit unusual properties on a cosmic scale if space itself forms a closed loop. In a looped universe, electromagnetic waves could potentially travel around the entire cosmos, eventually returning to their starting point. This could lead to intriguing phenomena, such as the possibility of seeing multiple images of the same distant object in different directions, as light from that object travels along different paths around the loop. Furthermore, the large-scale structure of a looped cosmos might affect the strength and behavior of magnetic fields on cosmic scales. We might observe unexpected patterns or alignments in the magnetic fields of galaxies and galaxy clusters that could be explained by the overall geometry of space. The interaction between electromagnetism and gravity, already a topic of intense study in physics, could become even more complex in a looped universe. The curvature of space-time on this grand scale might influence how electromagnetic forces propagate and interact with matter across vast distances, potentially leading to new insights into the fundamental nature of these forces. In a looped universe, the fundamental forces of nature, including the strong and weak nuclear forces, would likely behave in much the same way as they do in our observable universe. The strong nuclear force, responsible for binding quarks together to form protons and neutrons, and the weak nuclear force, involved in radioactive decay and nuclear fusion, are believed to operate consistently across the cosmos. However, the concept of a looped universe introduces some intriguing possibilities. If space were to curve back on itself, creating a closed loop, it might affect the large-scale distribution of matter and energy. This could potentially lead to subtle variations in how these forces manifest over vast distances. One fascinating consideration is how the looped structure might impact the uniformity of physical laws. In our current understanding, the laws of physics, including those governing the strong and weak nuclear forces, are thought to be constant throughout the universe. A looped universe might challenge this assumption, potentially introducing slight variations or gradients in force strengths across the loop. It is important to note that these ideas remain largely theoretical. Our current observations and experiments have not provided evidence for significant variations in the fundamental forces across the observable universe. The behavior of the strong and weak nuclear forces in a looped universe remains a subject of speculation and ongoing research in theoretical physics and cosmology. As we explore the fascinating concept of a looped universe, we must consider the intriguing possibility of new, unknown forces emerging from this cosmic structure. The idea of a universe that loops back on itself, potentially connecting distant regions of space and time, opens up a realm of possibilities that challenge our current understanding of physics. In such a looped universe, the very fabric of space-time might behave in ways we have yet to comprehend fully. This unique geometry could give rise to novel interactions between matter and energy, potentially manifesting as forces that are currently undetectable or unaccounted for in our existing models of the universe. These hypothetical new forces could have far-reaching implications for our understanding of fundamental physics. They might influence the behavior of particles at the quantum level or affect the large-scale structure of the cosmos. For instance, they could provide explanations for some of the mysteries that continue to puzzle scientists, such as the nature of dark matter and dark energy. However, it is important to note that while the concept of new forces emerging from a looped universe is captivating, it remains highly speculative. Scientists continue to search for evidence of such phenomena, using advanced observatories and experiments to probe the deepest reaches of the cosmos and the fundamental nature of reality itself. Quantum entanglement across vast distances in a looped universe presents a fascinating scenario that challenges our understanding of both quantum mechanics and cosmology. In such a universe, the very fabric of space-time curves back on itself, creating a closed loop rather than extending infinitely in all directions. When particles become entangled, they share a quantum state regardless of the distance between them. This connection appears to defy our classical understanding of information transfer, as changes to one particle instantaneously affect its entangled partner. In a looped universe, this phenomenon could have intriguing implications. Imagine two entangled particles separated by billions of light-years in a looped universe. They might actually be closer to each other in the opposite direction around the loop. This could potentially create situations where entanglement effects appear to travel faster than light when measured in one direction, but remain within light speed limits when considered along the shorter path around the universal loop. Furthermore, in a looped universe, entangled particles might even encounter themselves after traveling around the entire loop. This could lead to complex quantum interactions and potentially create closed time-like curves where cause and effect become blurred on a quantum scale. Such scenarios push the boundaries of our current theories and highlight the need for a unified understanding of quantum mechanics and gravity in cosmological contexts. Quantum tunneling is a fascinating phenomenon that occurs at the subatomic level, allowing particles to pass through barriers that classical physics would deem impossible. In the context of a cosmic loop, this concept becomes even more intriguing. While quantum tunneling is well established for particles, its application to larger scales, such as cosmic structures, remains highly speculative. The probability of quantum tunneling decreases rapidly with the size and mass of an object. For macroscopic objects or cosmic structures, the chances become vanishingly small. However, in the extreme conditions of the early universe or near singularities, the laws of physics as we know them break down. Some theories propose that in these extreme environments, quantum effects might manifest on larger scales. This could potentially allow for matter to jump between different points in a cosmic loop, though this idea remains purely theoretical. It is important to note that our understanding of how quantum mechanics interacts with gravity and large-scale structures is still limited. The search for a theory of quantum gravity continues, and it may provide new insights into how quantum effects might influence cosmic structures and the fabric of space-time itself. The uncertainty principle, a fundamental concept in quantum mechanics, would take on fascinating implications in a universe that loops back on itself. In such a cosmic structure, often called a closed or finite universe, the very nature of space and time would be altered, influencing how we understand particle behavior and measurement. In a looping universe, particles could potentially interact with themselves across vast cosmic distances. This self-interaction would add an extra layer of complexity to the already perplexing uncertainty principle. The position and momentum of particles might become even more challenging to pin down, as their past and future states could influence their present behavior. Moreover, in a finite universe, there would be a maximum possible distance between 2 points. This limitation could potentially affect the range of possible momentum values for particles, further complicating the uncertainty relationship. The interplay between position and momentum uncertainty might manifest in unexpected ways, possibly leading to new quantum phenomena unique to this cosmic geometry. The concept of quantum entanglement would also take on new dimensions in a looping universe. Particles could potentially be entangled with themselves across the universal loop, creating mind-bending scenarios where cause and effect become even more blurred than in our current understanding of quantum mechanics. This self-entanglement could lead to novel quantum effects and potentially alter our interpretation of the uncertainty principle in profound ways. Quantum fluctuations are indeed a fascinating aspect of the universe at its smallest scales. These minute variations in energy and matter could potentially influence the structure of cosmic strings, including any looped configurations they might form. At the quantum level, particles constantly pop in and out of existence, creating a dynamic and unpredictable environment. This quantum foam, as it is sometimes called, could interact with cosmic strings in ways that are not yet fully understood. In the context of maintaining or disrupting looped structures, quantum fluctuations might play a dual role. On one hand, these fluctuations could potentially help stabilize loops by providing small amounts of energy that counteract the tendency of loops to collapse or dissipate. The constant influx of quantum energy might act as a sort of support system, helping to keep the loop intact over longer periods. Conversely, quantum fluctuations could also serve as a disruptive force. If a fluctuation were to occur at just the right point along a cosmic string loop, it might introduce enough instability to cause the loop to break apart or change its configuration. This disruption could lead to the formation of new, smaller loops or even the straightening of the string. The interplay between quantum fluctuations and cosmic strings remains an area of active research in theoretical physics. As our understanding of both quantum mechanics and cosmic strings continues to evolve, we may gain new insights into how these fundamental aspects of the universe interact and shape the cosmos on both the smallest and largest scales. Quantum field theory, the foundational framework of particle physics, would require significant alterations to accommodate the concept of a looped universe. In such a scenario, the very fabric of space-time would possess a fundamentally different structure, challenging our current understanding of quantum fields and their interactions. One key modification would involve redefining the notion of vacuum states. In a looped universe, the lowest energy state of quantum fields might exhibit periodic behavior, reflecting the cyclic nature of space itself. This could lead to novel quantum phenomena and potentially alter our understanding of particle creation and annihilation processes. Furthermore, the concept of entanglement, a cornerstone of quantum mechanics, might need to be re-evaluated. In a looped universe, particles could potentially be entangled across vast cosmic distances or even multiple cycles of the universe. This could have profound implications for quantum information theory and our understanding of causality. Lastly, the mathematical formalism of quantum field theory would need to incorporate the topology of a looped universe. This could involve developing new mathematical tools to describe field interactions on curved closed manifolds, potentially leading to a more unified theory that bridges quantum mechanics and gravity in this unique cosmic setting. In a looped universe, the potential for life to evolve differently across various regions is a fascinating concept. The fundamental laws of physics would likely remain constant throughout the universe, but local conditions could vary significantly, leading to diverse evolutionary paths. Different regions might experience varying levels of cosmic radiation, gravitational influences, or chemical compositions. These factors could drive unique adaptations in potential life forms. For instance, in areas with higher radiation, organisms might develop more robust DNA repair mechanisms or protective outer layers. The looped nature of the universe could also introduce intriguing possibilities. As matter and energy cycle through the loop, they might create pockets of increased complexity or unusual elemental distributions. These localized differences could serve as catalysts for novel forms of life, perhaps based on alternative biochemistries we have yet to imagine. However, it is important to note that the existence of a looped universe remains a theoretical concept. While it presents exciting possibilities for the diversity of life, our current understanding of cosmology and biology is still evolving. The search for extraterrestrial life continues to challenge our assumptions and expand our perspective on what life might look like beyond Earth. Consciousness in a looped cosmic structure could experience profound alterations. In such a universe, time and space would not follow linear progression as we understand it, potentially leading to a cyclical nature of existence. This could result in consciousness experiencing repeated patterns or events, possibly without awareness of previous cycles. The very fabric of reality in a looped structure might blur the lines between past, present, and future. Consciousness could potentially access information or experiences from what we would consider different points in time simultaneously. This non-linear perception could drastically reshape how a conscious entity processes and interprets its surroundings and experiences. Furthermore, the concept of cause and effect might become distorted in a looped cosmic structure. Consciousness might struggle to distinguish between actions and their consequences, as events could potentially influence their own causes. This circular causality could lead to a fundamentally different way of perceiving reality and making decisions. Ultimately, consciousness in such a universe might develop a heightened sense of interconnectedness and unity with the cosmos. The boundaries between self and environment could become less distinct, potentially fostering a more holistic and integrated form of awareness that transcends our current understanding of consciousness. The concept of cosmic loops, also known as cyclic models of the universe, presents intriguing questions about the nature of information and memory across vast stretches of time and space. In these models, our universe undergoes a series of expansions and contractions, potentially repeating endlessly. The idea of preserving memories or information through these cycles is a fascinating one, but it faces significant challenges. Current scientific understanding suggests that information cannot survive the extreme conditions present at the end and beginning of each cosmic cycle. The immense energies and densities involved would likely destroy any conventional forms of data storage. However, some theoretical physicists have proposed speculative ideas about how information might persist. One such concept involves quantum entanglement, where particles remain connected even across vast distances. In theory, this quantum information might survive the transition between cycles. Another hypothesis suggests that fundamental constants of physics could carry imprints of previous universes, acting as a form of cosmic memory. While these ideas are captivating, they remain highly speculative and lack empirical evidence. The question of preserving memories across cosmic loops continues to challenge our understanding of physics and the nature of information itself, inspiring further research and philosophical contemplation about the ultimate fate of knowledge in our universe. In a looped universe, the concept of reincarnation would indeed take on fascinating new dimensions. Traditional notions of reincarnation often involve the rebirth of a soul or consciousness into a new body after death. However, in a universe that loops back on itself in time, the very nature of existence and rebirth could be fundamentally altered. Consider a universe that eventually contracts and restarts in a cyclic model. In this scenario, the entire cosmos would be reborn, not just individual beings. Every event, every life, and every moment would recur infinitely. This cosmic reincarnation would encompass the totality of existence, potentially giving new meaning to the idea of past lives and future incarnations. The implications for individual consciousness in such a universe are profound. One might speculate that our current existence is just one iteration in an endless cycle of universal rebirths. This could suggest that we have lived this exact life countless times before and will do so again in future cycles. The boundaries between past, present, and future lives would blur, as all moments would exist simultaneously across different iterations of the universe. However, it is crucial to note that these ideas remain speculative. While some cosmological models propose cyclical universes, there is currently no scientific consensus on whether our universe is indeed looped or cyclic. The concept serves as an intriguing thought experiment, challenging our understanding of time, existence, and the nature of consciousness itself. In a looped cosmos, beings would experience a fundamentally different reality from what we understand. Their perception of space and time would be radically altered as the very fabric of their universe would curve back on itself. Imagine traveling in what seems to be a straight line, only to find yourself back where you started. This is not just a thought experiment for inhabitants of a looped cosmos, it would be their lived reality. Their understanding of distance and direction would need to account for the fact that moving far enough in any direction could lead them back to their starting point. Time in such a universe might also loop, creating a cycle of recurring events. Inhabitants might experience déjà vu on a cosmic scale, potentially observing the same celestial events repeating at regular intervals. This could challenge their notions of cause and effect, as the end of one cycle could influence the beginning of the next. The concept of infinity would take on new meaning in a looped cosmos. While the universe might be finite in size, it could be traversed indefinitely. This could lead to profound philosophical and scientific questions about the nature of existence and the possibility of eternal recurrence. Beings in such a cosmos might develop unique perspectives on life, death, and the concept of progress, shaped by the cyclical nature of their reality. The concept of a universe that endlessly loops challenges our fundamental understanding of existence and raises profound philosophical questions. Such a universe, often called a cyclic or oscillating universe, suggests that our current reality is just one iteration in an infinite series of cosmic cycles. This idea dramatically alters our perception of time and causality. In an endlessly looping universe, the notions of beginning and end become meaningless. Every event, including our own lives, would repeat infinitely. This raises questions about free will and determinism. If everything is destined to repeat, do our choices truly matter, or are they predetermined by the cycles that came before? The concept also has implications for the nature of identity and consciousness. If the universe repeats exactly, does that mean we live the same life over and over, or do slight variations occur? This leads to questions about the continuity of self across cycles and whether our consciousness persists or is recreated anew each time. Furthermore, a looping universe challenges our understanding of progress and purpose. If everything ultimately returns to its starting point, what meaning can we ascribe to our actions and achievements? This concept could either lead to a sense of cosmic futility or inspire us to find meaning in the present moment, knowing that each experience is both unique and eternal. The idea of cosmic cycles repeating events challenges our traditional understanding of free will. If the universe undergoes a series of expansions and contractions, with each cycle potentially recreating similar or identical circumstances, it raises profound questions about the nature of choice and determinism. In this scenario, our actions and decisions might be predetermined by the cosmic cycle repeating in each iteration of the universe. This would suggest that our sense of free will is an illusion, as our choices are already set by the pattern of the cycle. However, even if events repeat, our perception of making decisions remains intact, allowing us to experience the illusion of free will in each cycle. Alternatively, one could argue that free will exists within the confines of each cycle. While the broad strokes of events might repeat, individual choices could still vary, creating unique experiences within the larger pattern. This perspective allows for a form of limited free will, where our decisions matter within the context of each cosmic iteration. Ultimately, the concept of repeating cosmic cycles adds a layer of complexity to the already challenging question of free will. It forces us to reconsider the nature of choice, determinism, and the very fabric of reality itself, pushing the boundaries of our understanding of consciousness and the universe. In a universe without a definitive beginning or end, the concept of existence takes on a profoundly different meaning. Traditional notions of purpose often stem from ideas of creation and finality, but in an eternal cosmos, we must reconsider our place within it. Such a universe challenges our understanding of causality and time itself. Without a clear starting point or ultimate conclusion, the very fabric of reality becomes an endless tapestry of interconnected events and phenomena. In this context, existence might be seen as an ongoing process of change and interaction rather than a journey from a fixed beginning to a predetermined end. The meaning of existence in such a universe could be found in the present moment and the connections we form. Each instant becomes a unique point in an infinite continuum, valuable for its own sake rather than as part of a grand narrative. The significance of our actions and experiences might lie in their immediate effects and the ripples they create through time and space, rather than in their relation to an overarching cosmic plan. This perspective invites us to embrace the inherent wonder of being part of an eternal cosmic dance. It encourages us to find meaning in exploration, discovery, and the constant unfolding of new possibilities within an infinite and ever-changing universe. The absence of a definitive beginning or end does not diminish the value of existence, but rather amplifies the importance of how we choose to exist in each moment of our infinite cosmic journey. In a looped cosmic system, the concepts of purpose and destiny take on intriguing new dimensions. Traditional notions of linear progress or a final endpoint become less relevant when the universe cycles through repeated iterations. This cyclical nature challenges our understanding of cause and effect, as events in one cycle could potentially influence or be influenced by occurrences in another. The idea of individual purpose might shift from achieving a specific end goal to playing a role in the ongoing cosmic dance. Each cycle could present opportunities for growth, learning, and evolution, with the accumulated wisdom potentially carried forward into subsequent iterations. This perspective might encourage a focus on the journey rather than the destination, as the destination becomes a new beginning. Destiny in a looped cosmos might be viewed as a complex interplay of recurring patterns and variations. Rather than a predetermined path leading to a final outcome, it could be seen as a series of interconnected events that ripple across multiple cycles. This view might foster a sense of cosmic interconnectedness, where actions and choices resonate beyond a single lifetime or even a single universal cycle. Ultimately, a looped cosmic system could inspire a profound re-evaluation of our place in the universe. It might lead us to consider our roles not just in the context of a single lifespan or even a single cosmic cycle, but as part of an endless, ever-evolving cosmic story. This perspective could dramatically alter our approach to existence, purpose, and the very nature of being. In a looped universe, the concept of eternity indeed takes on a fascinating new dimension. This cosmological model suggests that the universe might repeat itself endlessly, cycling through periods of expansion and contraction. Each cycle would essentially reset the universe, potentially recreating all matter and energy in a similar configuration. This looping nature challenges our traditional understanding of eternity. Instead of a linear progression stretching infinitely into the future, we would have a cyclical eternity. Time would still be infinite, but it would fold back on itself, creating a series of cosmic reboots. This idea raises intriguing questions about the nature of existence and reality. In such a universe, events and even individual lives might recur countless times. However, each cycle would likely have subtle differences, as quantum fluctuations and chaos theory suggest that exact repetition is improbable. This concept of eternal recurrence has profound implications for philosophy and our understanding of purpose and meaning in the cosmos. The looped universe theory also impacts our view of the far future. Rather than facing a cold, dark eternity, as in some other models, the universe would continually renew itself. This perpetual cycle of death and rebirth on a cosmic scale presents a different kind of forever, one that is dynamic and ever-changing, yet paradoxically repetitive. Cosmologists employ several sophisticated mathematical frameworks to explore the intriguing concept of looped universe scenarios. One prominent approach utilizes topology, the mathematical study of shapes and spaces. This framework allows scientists to model universes with complex geometries that could potentially loop back on themselves. Another key tool is general relativity, Albert Einstein's groundbreaking theory that describes how gravity shapes the fabric of space-time. Researchers use advanced equations from general relativity to investigate how matter and energy might behave in a universe with a looped structure. These equations help scientists understand how light and objects would travel in such a cosmos. Quantum mechanics also plays a crucial role in these models, especially when considering the behavior of the universe at extremely small scales or in its earliest moments. Some theories combine aspects of quantum mechanics with general relativity, leading to frameworks like loop quantum cosmology. This approach suggests the possibility of a bouncing universe that contracts and expands in cycles. Computer simulations have become invaluable in testing these mathematical models. Scientists use powerful supercomputers to run complex algorithms that simulate the evolution of looped universe scenarios over vast timescales. These simulations help researchers visualize and analyze the potential consequences of different topological structures on cosmic evolution and observable phenomena. Computer simulations have become invaluable tools in cosmology, allowing scientists to explore complex scenarios like the dynamics of a looped universe. These powerful computational models enable researchers to test theories and predict outcomes that would be impossible to observe directly. In the context of a looped universe, simulations help scientists investigate how matter and energy might behave in such a unique cosmic structure. By inputting various parameters and initial conditions, researchers can observe how galaxies, dark matter, and other cosmic components evolve over time within a closed, repeating space. These simulations also allow scientists to explore the potential observable consequences of a looped universe. For instance, they can model how light would travel in such a universe, potentially revealing patterns or anomalies in the cosmic microwave background radiation that could indicate a looped structure. Additionally, simulations can help predict how gravitational waves might propagate in a closed universe, providing another avenue for potential detection. Furthermore, computer models enable cosmologists to study how a looped universe might affect fundamental concepts like the expansion of space, the distribution of matter, and the ultimate fate of the cosmos. By comparing these simulated outcomes with real-world observations, scientists can refine their theories and gain deeper insights into the nature of our universe. Topology plays a crucial role in mathematically describing a looped cosmos, offering a framework to understand the shape and structure of the universe on the largest scales. In cosmology, topology helps scientists explore the possibility of a universe that connects back on itself, much like the surface of a donut, or a more complex three-dimensional shape. When considering a looped cosmos, topologists examine how space might be curved or folded in ways that allow it to connect with itself. This could result in a universe where traveling in one direction for a long enough distance might bring you back to your starting point, similar to how circumnavigating the Earth works on a much smaller scale. One intriguing aspect of topology in cosmology is its potential to explain certain large-scale observations of the universe. For instance, if space were indeed looped, it could account for patterns in the cosmic microwave background radiation that some scientists have observed. These patterns might be the result of light traveling multiple times around a looped universe. Topological models also allow cosmologists to explore the idea of a finite yet unbounded universe. This concept challenges our intuitive understanding of space and pushes the boundaries of how we conceive the cosmos, highlighting the power of mathematics to describe realities beyond our everyday experience. Chaos theory, when applied to a looped universe over immense timescales, reveals fascinating possibilities. In such a scenario, the universe would repeatedly cycle through periods of expansion and contraction, each cycle potentially lasting trillions upon trillions of years. The initial conditions of each new cycle would be influenced by the final state of the previous one, creating a complex feedback loop. This cosmic feedback mechanism could lead to unpredictable outcomes, a hallmark of chaotic systems. Even minute differences in the starting conditions of each cycle could result in dramatically different universes. These variations might manifest in altered distributions of matter and energy, different physical constants, or even changes to fundamental forces. Over an infinite number of cycles, The universe could explore every possible configuration allowed by the laws of physics. This concept, known as Poincaré recurrence, suggests that given enough time, the universe would eventually return to a state nearly identical to its starting point. However, the timescales involved would be so vast as to be almost incomprehensible. The application of chaos theory to a cyclic universe also raises intriguing questions about the nature of time and causality. Each cycle could be seen as both an effect of the previous cycle and a cause of the next, creating a cosmic version of the chicken and egg paradox. This interconnectedness across cycles challenges our linear understanding of time and causality, hinting at a deeper, more complex structure to reality than we currently comprehend. To fully describe a looped universe, scientists might need to develop entirely new branches of mathematics that go beyond our current understanding of geometry and topology. One potential concept could involve multi-dimensional manifolds that seamlessly connect across vast cosmic distances, creating pathways through space that appear to loop back on themselves. These mathematical models might incorporate elements of non-Euclidean geometry on a cosmic scale, allowing for the curvature of space-time to bend in ways that our conventional mathematics struggles to represent. Mathematicians and physicists might need to formulate new equations that can account for the behavior of matter and energy in a universe where traveling in one direction could eventually bring you back to your starting point. Another crucial aspect would be developing mathematical frameworks to describe how causality and time function in a looped universe. This could require new ways of representing temporal relationships that go beyond our linear understanding of past, present, and future. Such models might need to account for potential paradoxes or unusual phenomena that could arise in a universe where events could theoretically influence their own causes. Ultimately, describing a looped universe would likely require a synthesis of advanced concepts from quantum mechanics, general relativity, and cutting-edge mathematical theories. This new mathematics would need to elegantly unify these diverse fields while also introducing novel ideas that can accurately model the unique properties of a cosmos that loops back on itself. The fecund universes theory proposes that our universe might be capable of spawning new universes, much like a parent giving birth to offspring. This concept suggests that black holes could be the mechanism for this cosmic reproduction. When a black hole forms, it might create a new universe on the other side of its event horizon, separate from our own. This theory ties into the idea of cosmic loops in a fascinating way. Cosmic loops, also known as closed time-like curves, are theoretical paths in space-time that loop back on themselves. In the context of fecund universes, these loops could potentially connect parent and child universes, creating a network of interconnected realities. The fecund universes theory offers an intriguing explanation for the apparent fine-tuning of our universe. It suggests that universes might evolve and adapt over generations, with each new universe inheriting characteristics from its parent. Those universes with properties conducive to forming black holes would be more likely to reproduce, potentially leading to a form of cosmic natural selection. While highly speculative, this theory provides a thought-provoking framework for understanding the potential vastness and complexity of reality beyond our observable universe. It challenges us to consider the possibility that our universe might be part of a much larger, ever-expanding multiverse connected through a web of cosmic loops and black hole gateways. Lee Smolin's concept of cosmological natural selection presents an intriguing perspective on the evolution of universes, which can be related to the idea of a looped universe model. Smolin proposes that universes might reproduce through black holes, with each black hole potentially giving birth to a new universe with slightly different physical constants and laws. In the context of a looped universe model, where the universe goes through cycles of expansion and contraction, Smolin's idea could be integrated in fascinating ways. Each cycle of the universe could be seen as an opportunity for cosmic evolution, with the physical properties of the universe being fine-tuned through a process analogous to natural selection. As the universe contracts and potentially forms a singularity similar to a black hole, it might give rise to a new cycle with slightly altered characteristics. This process could allow for the optimization of universal constants over numerous cycles, potentially explaining why our current universe appears to be finely tuned for the existence of complex structures and life. However, it's important to note that both Smolin's concept and the looped universe model remain highly speculative. They are thought-provoking ideas that challenge our understanding of cosmic evolution and the nature of reality, but they currently lack definitive observational evidence to support them. The bubble universe theory proposes that our universe is just one of many universes existing within a larger multiverse structure. According to this concept, each universe forms as a bubble in an ever-expanding cosmic foam. These bubbles can grow, collide, and even merge with one another, creating a dynamic and ever-changing multiverse landscape. Incorporating loops into this theory adds another layer of complexity and intrigue. Some physicists suggest that within these bubble universes, spacetime might form closed loops or cyclic patterns. This means that instead of having a linear timeline with a clear beginning and end, time could potentially curve back on itself, creating a repeating cycle of events. These loops could manifest in various ways within the bubble universe framework. One possibility is that entire universes might undergo cycles of expansion and contraction, repeatedly growing and shrinking over vast periods. Another idea proposes that certain regions within a bubble universe could experience localized time loops, where events repeat in a specific area while the rest of the universe continues to evolve. The combination of bubble universes and loops presents a fascinating picture of reality. It suggests a multiverse filled with diverse cosmic structures, each potentially following its own unique patterns of space and time. This concept challenges our understanding of the nature of existence and opens up new avenues for exploring the fundamental fabric of reality. Eternal inflation and the concept of a looped universe are two distinct theories that attempt to explain the nature and structure of our cosmos, but they approach this task from different angles. Eternal inflation proposes that our universe is part of a much larger multiverse where new universes are constantly being created. In this model, space expands at an exponential rate, driven by the energy of a quantum field. As this rapid expansion occurs, quantum fluctuations can cause some regions to stop inflating and form bubble universes with their own physical laws and properties. This process continues indefinitely, hence the term eternal inflation. The looped universe theory, on the other hand, suggests that our universe follows a cyclical pattern of expansion and contraction. In this model, the universe expands from a singularity, reaches a maximum size, then contracts back to a singularity, only to expand again in a new cycle. This creates a loop in time, where the end of one universe becomes the beginning of the next. While these theories might seem incompatible at first glance, some physicists have proposed ways to reconcile them. One possibility is that each cycle in a looped universe could give rise to regions of eternal inflation, creating new bubble universes with each iteration. Alternatively, eternal inflation could potentially occur within a larger cyclical framework, with each loop spawning its own inflationary multiverse. The concept of interconnected cosmic structures extends far beyond our current observational capabilities, but theoretical models and emerging evidence suggest intriguing possibilities. Astronomers have already identified vast cosmic structures like galaxy filaments and supervoids, which form a cosmic web spanning billions of light years. These structures hint at even larger scale patterns in the universe. Recent studies propose that our observable universe might be part of a much grander cosmic landscape. Some theories suggest the existence of a multiverse where numerous universes coexist, potentially interconnected through higher dimensions or quantum entanglement. These connections could form intricate networks or loops on scales far surpassing our cosmic horizon. The idea of cosmic loops aligns with certain models of eternal inflation, where universes continually spawn new universes in an ever-expanding fractal pattern. In this scenario, our universe might be one bubble in a vast foam of realities, each with its own physical laws and constants. The boundaries between these universes could form complex, intertwining structures at the largest imaginable scales. While these concepts remain highly speculative, they drive ongoing research in cosmology and theoretical physics. Advanced gravitational wave detectors and next-generation space telescopes might provide new insights into these grand cosmic structures. As our understanding of the universe deepens, we may uncover evidence of even more complex and awe-inspiring cosmic architectures that challenge our current perceptions of reality. In a looped universe, advanced civilizations could potentially exploit its unique properties for remarkable feats of energy production and travel. One intriguing possibility is the creation of cosmic shortcuts. If space truly loops back on itself, these civilizations might discover paths that connect distant regions of the universe, allowing for rapid transit across vast cosmic distances. These hypothetical beings could also harness the cyclic nature of a looped universe for energy generation. By tapping into the enormous energies released during each cycle of universal collapse and rebirth, they might power their civilizations for eons. This concept, while speculative, draws parallels to how we currently use renewable energy sources on Earth. Furthermore, advanced civilizations in a looped universe might develop technologies to manipulate the very fabric of space-time. By understanding and controlling the mechanisms that cause the universe to loop, they could potentially create localized regions of closed time-like curves. These could serve as temporal highways, enabling travel to different epochs within the same universal cycle. However, it is crucial to note that the concept of a looped universe remains theoretical. Our current understanding of cosmology does not definitively support or refute this model. As we continue to explore the cosmos and push the boundaries of physics, we may uncover new insights that shed light on these tantalizing possibilities for advanced civilizations. The concept of a looped structure in the universe is an intriguing idea that has captured the imagination of scientists and science fiction writers alike. However, current scientific understanding does not support the existence of such a structure. Even if the universe were looped, it would not necessarily enable faster-than-light communication. Our best models of the universe, based on general relativity and observational evidence, suggest that the universe is flat and expanding. This expansion appears to be accelerating, making the idea of a looped structure even less likely. The vast distances between cosmic structures and the limitations imposed by the speed of light present significant challenges to any form of faster-than-light communication. While theoretical concepts like wormholes or quantum entanglement have been proposed as potential avenues for faster-than-light information transfer, these remain purely speculative. Wormholes, if they exist, would require exotic forms of matter and energy to stabilize them. Quantum entanglement, while a proven phenomenon, cannot transmit classical information faster than light, according to our current understanding. It is important to note that faster-than-light communication would violate the principle of causality, a fundamental aspect of our understanding of the universe. This principle states that cause must always precede effect, and its violation could lead to paradoxes that challenge our basic notions of reality. As such, the search for faster-than-light communication continues to be a subject of scientific inquiry and speculation, but remains firmly in the realm of theoretical physics for now. Time travel in a looped universe presents fascinating possibilities and challenges. In such a universe, where space and time curve back on themselves, the concept of past and future becomes more fluid. This cosmic structure could potentially allow for movement through time in ways our linear understanding struggles to grasp. One intriguing aspect of a looped universe is the possibility of closed time-like curves. These are paths through space-time that return to their starting point, not just in space, but also in time. If such curves exist, an object or person following this path could theoretically arrive back at their original time and place, effectively traveling through time. However, the existence of closed time-like curves raises significant paradoxes. The most famous is the grandfather paradox, where a time traveler could potentially prevent their own birth by altering past events. In a looped universe, this paradox becomes even more complex, as cause and effect could form an endless cycle with no clear origin. Some theories suggest that the laws of physics might prevent such paradoxes from occurring, making certain types of time travel impossible. Others propose that time travel in a looped universe might only allow for journeys that maintain the consistency of events, preventing any changes to the established timeline. This concept, known as the Novikov self-consistency principle, suggests that time travelers would be unable to alter the past in ways that create paradoxes. As we explore the vastness of space, our technology continues to push the boundaries of what we can observe. Currently, our view of the universe is limited by the cosmic horizon, the farthest distance from which light has had time to reach Earth since the beginning of the universe. This horizon defines our observable universe, but it does not necessarily represent the entire cosmos. Advanced telescopes and detection methods have allowed us to peer deeper into space than ever before, capturing light from galaxies that existed when the universe was in its infancy. However, seeing beyond our local region of the cosmic web presents significant challenges. The expansion of space itself stretches light, making distant objects appear fainter and redder, eventually rendering them undetectable by conventional means. To overcome these limitations, scientists are developing innovative technologies. Gravitational wave detectors, for instance, can detect ripples in space-time caused by cosmic events, potentially allowing us to hear phenomena beyond our visual reach. Neutrino detectors offer another avenue, as these elusive particles can travel vast distances unimpeded, carrying information from regions beyond our current observational limits. Future advancements in quantum technologies and artificial intelligence may also play a crucial role in extending our cosmic vision. These tools could help us process and interpret signals that are currently too weak or complex for our instruments to decipher, potentially unveiling hidden aspects of the universe that lie just beyond our current grasp. In a universe governed by the laws of physics as we understand them, several intriguing concepts for loop engines or devices have been proposed by scientists and theorists. One fascinating possibility is the Alcubierre drive, a theoretical propulsion system that could potentially enable faster-than-light travel. This concept involves creating a bubble of space-time around a spacecraft, contracting space in front of the vessel and expanding it behind, effectively moving the ship through space without violating relativity. Another concept is the Tipler cylinder, a massive rotating cylinder that might allow for closed time-like curves, theoretically enabling time travel. While highly speculative, this idea explores the potential for manipulating space-time through extreme gravitational effects. Similarly, wormholes, often depicted as tunnels or shortcuts through space-time, could theoretically function as a type of loop device, connecting distant points in space or even different times. Quantum loop engines, while not yet fully realized, are another area of exploration. These devices could potentially harness quantum effects to create novel forms of propulsion or energy generation. For instance, some theories propose using quantum entanglement to transmit information or even matter instantaneously across vast distances. Lastly, perpetual motion machines, though impossible according to our current understanding of thermodynamics, continue to captivate the imagination. While true perpetual motion remains firmly in the realm of science fiction, scientists continue to explore ways to minimize energy loss and maximize efficiency in various systems, pushing the boundaries of what is possible within the laws of physics. The concept of a looped universe is a fascinating theoretical model in cosmology, but it doesn't necessarily imply that events and histories repeat exactly. This idea, known as the closed time-like curve, suggests that the universe might curve back on itself in higher dimensions, creating a loop in space-time. However, even if the universe were shaped like a loop, it wouldn't guarantee an exact repetition of events. The universe is incredibly complex, with countless variables and interactions at play. Quantum mechanics introduces an element of fundamental uncertainty at the smallest scales, which could lead to different outcomes even if the initial conditions were similar. Moreover, the sheer scale of the universe means that even if it were to loop, the time involved would be so vast that any potential repetition would occur over timescales far beyond human comprehension. The current age of the universe is estimated to be around 13.8 billion years, and a hypothetical loop would likely span a much longer period. It's important to note that the idea of a looped universe remains highly speculative. Current observational evidence supports a flat or open universe model rather than a closed one. As our understanding of cosmology evolves, we continue to explore these intriguing possibilities, pushing the boundaries of our knowledge about the nature and shape of the universe. As the cosmic cycle repeats, subtle differences can emerge in each iteration. These variations might stem from quantum fluctuations at the smallest scales, influencing how matter and energy distribute during the expansion phase. The precise arrangement of galaxies and large-scale structures could differ slightly each time, like shuffling a cosmic deck of cards. Fundamental constants of nature might also experience minute shifts between cycles. The strength of gravity, the speed of light, or the properties of subatomic particles could vary by infinitesimal amounts, leading to subtly different physical laws governing each new universe. The interplay between dark matter and dark energy might evolve over multiple cycles, affecting the rate of expansion and the formation of cosmic structures. This could result in universes with varying lifespans or different distributions of matter and energy. These slight variations could accumulate over countless iterations, potentially leading to dramatically different outcomes in the long term. While each cycle might appear nearly identical at first glance, these small changes could be the seeds of cosmic diversity, ensuring that no two iterations of the universe are ever exactly the same. The concept of cosmic loops, often referred to as cyclic models of the universe, presents intriguing questions about the nature of consciousness and memory. In these models, the universe undergoes a series of expansions and contractions, potentially repeating endlessly. However, the preservation of consciousness or memory across such cycles faces significant challenges. Our current understanding of consciousness is deeply tied to the physical structures of our brains and the laws of physics in our universe. As the universe contracts and reaches extreme conditions in a potential Big Crunch scenario, the very fabric of space and time would be altered. The intense gravitational forces and energy densities would likely destroy all known forms of matter and energy, including any physical substrates that might store consciousness or memories. Moreover, if a new cycle of the universe were to begin, it would likely reset all physical parameters and initial conditions. This reset would erase any potential for information transfer between cycles, making it extremely improbable for any form of consciousness or memory to persist. The laws of physics and the fundamental constants that govern our reality might even be different in subsequent cycles, further complicating the possibility of continuity. While some speculative theories propose the existence of higher dimensions or parallel universes that might allow for the preservation of information across cosmic cycles, these ideas remain highly theoretical and lack empirical evidence. For now, the question of retaining awareness or memory across cosmic loops remains in the realm of philosophical speculation rather than scientific certainty. Encountering alternate versions of ourselves in different parts of a cosmic loop would have profound implications for our understanding of reality and identity. This scenario suggests the existence of a multiverse or parallel universes, where different versions of ourselves have made different choices or experienced different circumstances. One major implication would be the confirmation of the many worlds interpretation of quantum mechanics. This theory proposes that all possible alternate histories and futures are real, each representing an actual world or parallel universe. Meeting our alternates would provide tangible evidence for this mind-bending concept. Such encounters would also challenge our notion of free will and determinism. We might discover versions of ourselves who made different life choices. raising questions about the nature of decision-making and the role of chance in shaping our lives. This could lead to deep philosophical debates about the nature of consciousness and the self. Furthermore, these meetings could provide unprecedented opportunities for scientific and personal growth. We could learn from our alternate selves, gaining insights into different life paths, scientific discoveries, or technological advancements that our own timeline might have missed. However, such interactions could also lead to psychological distress, identity crises, or even conflicts between different versions of ourselves, each believing their reality to be the prime or correct one. In a looped universe scenario, the concept of eternal return takes on a fascinating dimension. This idea suggests that if the universe follows a cyclical pattern of expansion and contraction, everything that has ever happened might occur again in exactly the same way, infinitely. Imagine our universe expanding to its fullest extent, then collapsing back in on itself in a big crunch, only to be reborn in another big bang. In this model, the same stars, planets, and even living beings could potentially form again and again, repeating their entire existence in each cycle. This cosmic recycling would mean that you, listening to this very explanation, might have done so countless times before and will do so countless times again. Every decision, every chance encounter, every moment of joy or sorrow could be destined to replay endlessly throughout eternity. However, it is important to note that this concept remains highly speculative. While it presents an intriguing philosophical puzzle, current scientific observations do not support the idea of a cyclical universe. Most evidence points to an ever-expanding cosmos, making the notion of eternal return in a looped universe an engaging thought experiment rather than a likely reality. As we venture to the farthest reaches of the observable universe, the concept of an edge where the cosmos loops back on itself presents a fascinating possibility. This idea stems from the theory that our universe might have a finite size and a specific shape, potentially allowing it to connect back to itself in ways that challenge our usual understanding of space. If such an edge exists, we might encounter phenomena that defy our current laws of physics. Light and matter could exhibit strange behaviors, potentially appearing to repeat or mirror themselves as they traverse this cosmic boundary. We might observe galaxies or other large-scale structures that seem to be duplicated or distorted, creating a cosmic hall of mirrors effect. At this hypothetical boundary, the very fabric of space-time could warp and bend in extraordinary ways. The distinction between here and there might become blurred, with objects potentially existing in multiple locations simultaneously. This could lead to mind-bending scenarios where traveling in one direction might bring you back to your starting point from the opposite side. It is important to note that while these ideas are intriguing, they remain highly speculative. Current observations have not provided evidence for such a cosmic topology, and many scientists believe the universe might be infinite or at least vastly larger than our observable portion. Nevertheless, exploring these concepts pushes the boundaries of our understanding and drives us to seek new ways to probe the nature of our cosmos. As we explore the fascinating concept of cosmic loops, we might wonder about the nature of transitions between these vast cycles. The idea of a boundary layer or transitional zone between loop iterations is an intriguing possibility to consider. In our current understanding of cosmology, the universe appears to be expanding continuously. However, some theories propose that this expansion might eventually reverse, leading to a big crunch followed by another big bang. If such a cycle were to occur, there could indeed be a period of transition between the end of one universe and the beginning of the next. This transitional phase might be characterized by extreme conditions unlike anything we observe in our current universe. It could involve a complete breakdown of the laws of physics as we know them, or perhaps a state of pure energy before matter begins to form again. Some speculative models suggest that information or even fundamental constants might be passed from one iteration to the next through this boundary layer. However, it's important to note that the existence of cosmic loops and any transitional zones between them remains highly speculative. Current observational evidence supports a continuously expanding universe, and the concept of cyclic universes faces significant theoretical challenges. As our understanding of cosmology advances, we may gain new insights into these profound questions about the nature and history of our universe. Near the looping point of the universe, our understanding of physics could be dramatically challenged. The fundamental forces that govern our reality might behave in unexpected ways, potentially blurring the lines between gravity, electromagnetism, and the strong and weak nuclear forces. Time and space, which we typically consider as separate dimensions, could become intertwined in complex ways, making it difficult to distinguish between past, present, and future. The very fabric of space-time might stretch and warp to extreme degrees, potentially creating conditions where cause and effect no longer follow a linear path. Particles could exhibit properties that defy our current models, perhaps existing in multiple states simultaneously or moving in ways that contradict our understanding of quantum mechanics. Energy and matter might undergo transformations that are impossible under the laws of physics as we know them. The conservation of energy, a cornerstone of our current physical models, could be challenged or redefined. Exotic forms of matter and energy might emerge, possessing properties that are entirely foreign to our current scientific framework. These profound changes in the behavior of physical laws could have far-reaching implications for the structure and evolution of the universe. The formation of galaxies, stars, and planets might follow entirely different patterns, potentially giving rise to cosmic structures and phenomena that are beyond our current ability to imagine or detect. As matter and energy approach the looping threshold, they enter a realm where the laws of physics as we know them begin to break down. This boundary marks the point where our current understanding of the universe reaches its limits. When crossing this threshold, matter and energy would experience extreme conditions unlike anything observed in the known cosmos. The immense gravitational forces at play would stretch and compress matter to an unprecedented degree. Atoms would be torn apart, and even subatomic particles would be subjected to forces that could alter their very nature. The intense energy density at the threshold could potentially transform matter into pure energy, following Einstein's famous equation that relates mass and energy. Energy itself would be warped and distorted as it crosses the threshold. The fabric of space-time would be so severely curved that light might travel in loops or even become trapped. Time as we understand it could cease to have meaning, with cause and effect potentially occurring in reverse or simultaneously. The looping threshold represents a boundary beyond which our current theories of physics cannot accurately predict outcomes. It's possible that entirely new forms of matter and energy could emerge, governed by as yet undiscovered laws of nature. This makes the looping threshold not just a limit of our universe, but also a frontier of scientific exploration and understanding. As we explore the concept of a connected universe, we must consider the intriguing possibility of observable phenomena at the boundaries where our cosmos might loop back on itself. If the universe were indeed finite and connected, these regions could exhibit unique characteristics that set them apart from other areas of space. One potential phenomenon we might observe is a form of gravitational lensing unlike anything seen elsewhere. Light from distant galaxies could be bent and distorted in complex ways as it travels through these connection points, creating unusual patterns or duplicate images of the same celestial objects. Astronomers might detect multiple versions of a single galaxy or star cluster, each appearing at different angles or distances due to the universe's peculiar geometry at these junctions. Another possibility is the existence of cosmic strings, theoretical defects in the fabric of spacetime that could be more prevalent in these connecting regions. These strings, if they exist, might cause noticeable disruptions in the cosmic microwave background radiation or create distinctive gravitational wave signatures that our detectors could potentially identify. Furthermore, we might observe unexpected correlations between opposite sides of the observable universe. patterns in the distribution of galaxies or in the cosmic microwave background could show surprising symmetries or repetitions, hinting at a hidden connection between seemingly distant parts of the cosmos. Such observations would challenge our understanding of the universe's structure and could provide compelling evidence for a connected or finite universe model. In a looped universe, the evolution of galaxies, stars, and planets would take on fascinating new dynamics. As space curves back on itself, matter and energy would circulate in complex patterns, potentially altering the fundamental processes of cosmic structure formation. Galaxies in this scenario might experience repeated encounters with their own distant parts, leading to unique gravitational interactions. This could result in more frequent galaxy mergers and unusual shapes, as the same collection of stars and gas clouds might interact with itself across vast distances. The recycling of material through the loop could also influence star formation rates, possibly leading to extended periods of starburst activity or, conversely, premature galaxy aging. Stars within these looped galaxies might find themselves in gravitational environments unlike those in our observable universe. The cumulative effects of gravity from multiple directions could alter stellar orbits and potentially affect the stability of star systems. This could lead to more chaotic stellar motions and possibly impact the frequency of close stellar encounters, which in turn could affect the formation and survival of planetary systems. Planets forming in this looped cosmos would face unique challenges. The altered gravitational landscape could affect planetary migration patterns within protoplanetary disks, potentially resulting in more diverse planetary system architectures. The recycling of material through the universal loop might also influence the chemical composition available for planet formation, possibly leading to exotic types of planets not seen in our current understanding of the universe. The concept of cosmic loops or cyclical universes raises intriguing questions about the persistence of life and civilizations across vast stretches of time. While our current understanding of physics does not provide definitive answers, some theories suggest tantalizing possibilities. In models of a cyclic universe, where big bangs and big crunches alternate eternally, the conditions between cycles might be too extreme for any life forms to survive intact. The immense energies and gravitational forces involved would likely obliterate all existing structures, from the largest galaxies down to subatomic particles. However, some speculative ideas propose that information or patterns might potentially carry over from one cycle to the next. This could theoretically include the fundamental laws of physics or even more complex structures encoded in the fabric of spacetime itself. If such a mechanism existed, it might allow for the possibility of life or civilizations to be reborn in subsequent cycles, albeit in forms we might not recognize. Another perspective considers the multiverse theory, where our universe is one of many. In this scenario, civilizations might find ways to traverse or communicate between different universe bubbles, effectively persisting across multiple cosmic realms. While purely theoretical, these ideas push the boundaries of our imagination and drive further scientific inquiry into the nature of our cosmos and the potential for life within it. The idea of a periodically resetting universe would fundamentally alter our understanding of cosmic evolution. Instead of a linear progression from the Big Bang to the present day, we would need to consider a cyclical model where the universe goes through phases of expansion, contraction, and rebirth. In this scenario, each cycle of the universe might begin with its own version of the Big Bang, followed by the formation of galaxies, stars, and planets. As the cycle progresses, these structures would evolve and change, much like in our current model. However, the key difference lies in what happens at the end of each cycle. Rather than facing a potential heat death or big freeze, the universe would instead reach a point of reset. This could involve a big crunch, where all matter collapses back into a singularity, or perhaps a more exotic mechanism that essentially reboots the cosmos. After this reset, a new cycle would begin, potentially with different initial conditions or physical laws. This cyclic model raises intriguing questions about the nature of time, causality, and the potential for information or patterns to persist across cycles. It challenges our notions of cosmic history and the uniqueness of our current universe, suggesting that what we observe might be just one iteration in an endless series of universal cycles. As we explore the possibility of a cyclical universe, we must consider whether remnants from previous cosmic cycles could persist through the Big Bang. Some theoretical physicists propose that certain large-scale structures in our universe might carry imprints or echoes from earlier iterations of cosmic evolution. These hypothetical remnants, often referred to as cosmic fossils, could potentially be detected in the cosmic microwave background radiation or in the distribution of galaxies across the observable universe. For instance, some researchers suggest that anomalies in the cosmic microwave background, such as unexpected cold spots or alignments, might be evidence of collisions between our universe and others in a multiverse scenario. Another intriguing possibility is that the largest structures in our cosmos, like galaxy superclusters or cosmic voids, could retain some memory of previous universal cycles. The idea is that these enormous structures might be too vast to have formed entirely within the current age of our universe, hinting at a legacy from earlier cosmic epochs. However, it is crucial to note that these ideas remain highly speculative. The concept of a cyclical universe faces significant challenges, including how information or structure could survive the extreme conditions of a big crunch or big bounce. As our observational techniques and theoretical models advance, we may uncover more clues about the history and nature of our cosmos, potentially revealing evidence of past universal cycles hidden in the fabric of space and time. The concept of a looped universe presents intriguing possibilities for the long-term fate of matter and energy. In this scenario, rather than expanding indefinitely or collapsing back on itself, the universe would form a closed loop in space and time. This configuration could have profound implications for the ultimate destiny of everything within it. One significant consequence of a looped universe is that matter and energy might never truly be lost or destroyed. Instead, they would continually cycle through different states and configurations. As the universe completes each loop, the arrangement of galaxies, stars, and other cosmic structures could potentially reset, leading to a perpetual cycle of creation and destruction on a cosmic scale. This cyclical nature could also impact the effects of entropy, the tendency of systems to move towards disorder. In a looped universe, the increasing entropy that we observe might be balanced by periods of decreasing entropy as the universe approaches the end of each loop. This could result in a cosmic renewal where the universe periodically returns to a more ordered state. Furthermore, a looped universe might allow for the preservation of information across cosmic cycles. While individual objects and structures would be destroyed and recreated, the fundamental patterns and laws governing the universe could persist. This continuity might enable the universe to maintain a form of cosmic memory, potentially influencing the evolution of matter and energy in subsequent cycles.